अब इसका आगे अगला क्वेश्चन है कि ट्रांसवर्स वेव प्रोपगेटिंग अलोंग द एक्स एक्सिस रिप्रेजेंटेड बाय वाई एक्स कॉमा टी इट फाइंड 0.5 pi x minus 4 pi t minus pi by 4 where x in the meter and t is in the second। तो स्पीड ऑफ द वेव है जो कितना हो जाएगा, तो गिवन इक्वेशन दिया हुआ बाई एक्स कॉमा टी इक्वल टू 8 फाइंड 0.5 pi x minus 4 pi t minus pi by 4। इसको कंपेयर करेंगे स्टैंडर्ड इक्वेशन बाई इक्वल टू फाइंड के एक्स माइनस ओमेगा टी प्लस 5 है, तो ये एम्पलीट्यूड है, के है जो प्रोपगेशन कांस्टेंट, ओमेगा जो है एंगुलर फ्रीक्वेंसी है, तो क्या आ जाएगा 0.5 पाई, ओमेगा आ जाएगा 4 पाई। तो स्पीड ऑफ द ट्रांसफर हो जाएगा v इक्वल टू ओमेगा बाई के यानी कि 4 पाई बाई 0.5 पाई यानी कि आ जाएगा 8 मीटर पर सेकंड। इसका आंसर कितना जाएगा, आंसर आएगा ऑप्शन डी 8 मीटर पर सेकंड। नेक्स्ट है कि पॉइंट फोर्स emit sound equally in all direction in a non-observing medium. Two points P and Q are at a distance of the 2 meter and 3 meter respectively from the source. The ratio of the intensity of the wave at P and Q कितना हो जाएगा, इंटेंसिटी ऑफ द साउंड I इक्वल टू पी बाई 4 पाई आर स्क्वायर, जहाँ पी प्रेशर ऑफ द साउंड वेव है, आर जो है डिस्टेंस बिटवीन द साउंड एंड द पॉइंट है, तो आई जो होता है इनवर्सली प्रोपोर्शनल टू 1 बाई आर स्क्वायर होता है, यानी I1 बाई R2 हो जाएगा R2 बाई R1 का होल स्क्वायर, R1 जो है 2 मीटर है, R2 जो है 3 मीटर है, तो I1 बाई R2 हो जाएगा 3 बाई 2 का होल स्क्वायर यानी कि 9 बाई 4। इसका आंसर कितना जाएगा, ऑप्शन ए 9 बाई 4। फिर आता है द फेज डिफरेंस बिटवीन द टू वेव्स रिप्रेजेंटेड बाय y1 इक्वल टू 10 × 10⁻⁶ फाइन 40 प्लस x बाई 50 प्लस 0.5 मीटर और y2 इक्वल टू 10⁻⁶ cos 40 प्लस x बाई 10 x बाई 50 मीटर। तो अगर यहाँ से निकाल लें वेयर x इज एक्सप्रेस्ड इन द मीटर एंड t इज एक्सप्रेस्ड इन द सेकंड इज अप्रॉक्सिमेटली, तो y1 इक्वल टू 10⁻⁶ फाइन 40 प्लस x बाई 50 प्लस 0.5 मीटर, y2 इक्वल टू 10⁻⁶ cos 40 प्लस x बाई 50 मीटर, तो y2 इक्वल टू 10⁻⁶ फाइन 40 प्लस x बाई 50 प्लस 5 बाई 2 यानी फाइन पाई बाई 2 प्लस थीटा इक्वल टू कॉस थीटा। तो फेज डिफरेंस बिटवीन द वेव हो जाएगा डेल्टा फाइव इक्वल टू पाई बाई 2 माइनस 2.5 यानी 3.14 बाई 2 माइनस 0.5 यानी कि आ जाएगा 1.07 रैड। तो गिवन वेव आर फाइन एंड द कोसाइन फंक्शन फॉर दे आर प्लेन प्रोग्रेसिव हार्मोनिक वेव। इसके बाद फिर आता है कि वेव ऑफ द एम्पलीट्यूड ए इक्वल टू 0.2 मीटर, वेलोसिटी v इक्वल टू 350 मीटर पर सेकंड एंड वेवलेंथ 50 मीटर ट्रैवलिंग अलोंग द पॉजिटिव एक्सिस, देन द करेक्ट एक्सप्रेशन फॉर द वेव है जो क्या हो जाएगा, द जनरल एक्सप्रेशन फॉर द ट्रैवलिंग वेव कैन बी रिटन बाय इक्वल टू f ओमेगा t प्लस माइनस kx फॉर द ट्रैवलिंग वेव अलोंग द पॉजिटिव एक्सिस, we should use the minus sign only, तो बाय इक्वल टू f ओमेगा t माइनस kx, तो ओमेगा इक्वल टू 2 पाई v बाई लैम्डा यानी कि k इक्वल टू 2 पाई बाई लैम्डा, तो y इक्वल टू f 2 पाई बाई लैम्डा vt माइनस x, तो यहाँ से निकालेंगे तो a इक्वल टू 0.2 मीटर, b इक्वल टू 350 मीटर पर सेकंड, लैम्डा इक्वल टू 50 मीटर, तो y इक्वल टू 0.2 फाइन 2 पाई बाई 50 350 t माइनस x, तो y इक्वल टू 0.2 फाइन 2 पाई 50 माइनस x बाई 50 आ जाएगा। तो इसका आंसर कितना जाएगा, इसका आंसर आएगा ऑप्शन सी y इक्वल टू 0.2 फाइन 2 पाई 50 माइनस x बाई 50। फिर आता है कि द इक्वेशन ऑफ ए वेव गिवन बाय y इक्वल टू फाइन 40 माइनस x बाई 10 वेयर x बाई r इन द मीटर एंड t इन द सेकंड, तो वेलोसिटी ऑफ द वेव कितना हो जाएगा, तो गिवन वेव इक्वेशन इज ए y इक्वल टू फाइन 40 माइनस x बाई 10, तो ओमेगा इक्वल टू हो जाएगा 100 और k इक्वल टू जाएगा 1/10, तो v इक्वल टू हो जाएगा ओमेगा k यानी कि 100 बाई 1/10 यानी कि आ जाएगा 1000 मीटर पर सेकंड, तो आंसर आएगा ऑप्शन डी 1000 मीटर पर सेकंड। नेक्स्ट है कि वेव एंटर्स टू द वाटर फ्रॉम द एयर इन एयर फ्रीक्वेंसी wavelength, intensity and velocity are the n1, lambda 1, I1 and the v1 respectively. In the water, the corresponding quantity are the n2, lambda 2, I2 and the v2 respectively. तो फ्रीक्वेंसी है जो सेम रहेगा कि when the water enters from the one medium to another, its frequency remains unchanged. तो n1 इक्वल टू n2 हो जाएगा, बट वेवलेंथ, इंटेंसिटी एंड वेलोसिटी है जो चेंज हो जाता है, तो आंसर आएगा ऑप्शन बी कि n1 इक्वल टू n2। Next, two strings A and B have the length IA and IB and carry mass MA and MB at their lower ends. The upper ends being supported by the rigid support. If NA and the NB are the frequency of the vibration NA equal to NB, then तो यहाँ से अगर निकालें तो the frequency of the vibration of the string N is equal to 1/2 root over G by L, where NA is equal to 2NB, तो 1/2 root over G by IA equal to हो जाएगा 2.12 root over G by IB, तो 1 by IA equal to 4 by IB, तो IB equal to हो जाएगा 4IA। तो it is obvious from the equation 1 that frequency of the vibration of the string does not depend upon their massage, तो आंसर आएगा ऑप्शन बी कि IB is equal to हो जाएगा 4IA, तो regardless of the mass। नेक्स्ट है in a sinusoidal wave the time required for a particular point to move from the maximum displacement to zero displacement is 0.17 second। the frequency of the wave कितना हो जाएगा, if t the time period then the time required for a point to move from the maximum displacement to zero displacement is t/4 equal to 0.17 और t इक्वल टू 0.17 गुना 4 तो 0.68 आ जाएगा, तो देयरफॉर द फ्रीक्वेंसी ऑफ द वेव आ जाएगा n इक्वल टू 1/t यानी कि 1.47, तो इसका आंसर आएगा ऑप्शन ए 1.47 हर्ट्ज। अगला सवाल है कि ट्रांसवर्स वेव इज रिप्रेजेंटेड बाय द इक्वेशन y इक्वल टू बाय नॉट फाइन 2 पाई बाय लैम्डा vt माइनस x for height value of lambda is the maximum particle velocity equal to the 2 times the wave velocity. The given wave equation is y equal to by naught find 2 pi by lambda vt minus x. It is the in the wave equation v the particle velocity differentiating equation 1 with respect to 2 u is equal to dy by dt and by naught 2 pi v by lambda cos 2 pi vt by lambda आ जाएगा. तो maximum particle velocity आ जाएगा u max equal to by naught 2 pi v by lambda. Not given that maximum particle velocity equal to into wave velocity यानी by naught 2 pi v by lambda equal to 2v. तो लैम्डा इक्वल टू आ जाएगा पाई इंटू बाय नॉट. तो इसका आंसर कितना जाएगा? इसका आंसर आएगा ऑप्शन डी पाई इंटू बाय नॉट. नेक्स्ट है कि द इक्वेशन ऑफ ए साउंड वेव इज गिवन एज बाय इक्वल टू 0.005 फाइंड 52.4 x प्लस 316 t. द वेवलेंथ ऑफ दिस वेव कितना हो जाएगा? तो इक्वेशन फॉर द प्लेन प्रोग्रेसिव हार्मोनिक वेव इज बाय इक्वल टू एफ एन ओमेगा टी प्लस के एक्स है. गिवन इक्वेशन इज बाय इक्वल टू 0.005 फाइंड 52.4 x प्लस 316 t. तो ओमेगा इक्वल टू 316 के इक्वल टू 52.4 तो के इक्वल टू 2 पाई बाय लैम्डा यानी 52.4. तो लैम्डा इक्वल टू 0.1 यूनिट आएगा. तो इसका आंसर कितना आ जाएगा? ऑप्शन डी 0.1 यूनिट. नेक्स्ट है कि व्हाट इज द इफेक्ट ऑफ द ह्यूमिडिटी ऑन द साउंड वेव व्हेन ह्यूमिडिटी इंक्रीजेज. तो स्पीड ऑफ द साउंड वेव क्या होता है? इंक्रीज होता है ह्यूमिडिटी के इंक्रीज होने से, क्योंकि प्रेजेंस ऑफ द वाटर वेपर इन द एयर चेंज द डेंसिटी इफ यू बाय द वेलोसिटी ऑफ द चेंज इन द विद ह्यूमिडिटी ऑफ द एयर. मान लो कि रो एम है जो डेंसिटी ऑफ द मॉइस्ट एयर है, रो डी जो है डेंसिटी ऑफ द ड्राई एयर है, वी एम डेंसिटी ऑफ द साउंड इन द मॉइस्ट एयर है और वी टी जो है वेलोसिटी ऑफ साउंड इन द ड्राई एयर है. तो जो द इफेक्ट ऑफ द ह्यूमिडिटी ऑन द गामा इज नेग्लिजिबल एंड वेलोसिटी ऑफ द वेव इन द मीडियम इज गिवन बाय वी एम इज इक्वल टू रूट ओवर गामा पी बाई रो एम. गामा जो है इलास्टिसिटी ऑफ द मीडियम है, रो एम जो है डेंसिटी ऑफ द मीडियम है, रो जो है प्रेशर ऑफ द साउंड वेव है. तो वी डी इक्वल टू रूट ओवर गामा पी बाई रो डी. तो डिवाइडिंग वी गेट वी एम बाई वी टी इक्वल टू रूट ओवर गामा डी बाई गामा एम. The presence of the water vapor to different density of the air यानी कि rho d is less than rho m and the velocity of the sound in the moist air is greater than the velocity of the sound in the dry air. अगला सवाल है कि the speed of the wave in the medium is 560 meter per second. If 36 waves are passing through a point in the medium in 2 minutes, then the wavelength कितना हो जाएगा? तो given the speed of the wave 560 meter per second, number of wave दिया हुआ 3600, टाइम दिया हुआ t by 2 मिनट यानी 2 गुना 50 120 सेकंड. फ्रीक्वेंसी ऑफ वेव म्यू इक्वल टू टोटल नंबर ऑफ वेव फॉर टाइम टेकन यानी 36/120 यानी 30 वाट जो हो गया. तो वेवलेंथ ऑफ द वेव हो जाएगा लैम्डा इक्वल टू बी बाई म्यू यानी 760/30 यानी कि 25.3. तो आंसर आएगा ऑप्शन बी 25.3. फिर आता है कि हॉस्पिटल यूज एन अल्ट्रासोनिक स्कैनर टू लोकेट ट्यूमर्स इन टिश्यू. द ऑपरेटिंग फ्रीक्वेंसी ऑफ द स्कैनर इज 4.2 मेगाहर्ट्ज. द स्पीड ऑफ द साउंड इन द टिश्यू इज 1.1 किलोमीटर पर सेकंड. द वेवलेंथ ऑफ द साउंड इन द टिश्यू कितना हो जाएगा? The wavelength of the wave in the is the length of on the one wave it is equal to the distance traveled by the wave during the complete cycle. The wavelength of a wave is given by lambda equal to b by mu. जहाँ भी velocity of the wave sound है, mu जो है frequency of the wave है sound है. तो v 3 गुना 1.7 गुना 3 मीटर पर सेकंड, mu 1.4.2 गुना 10⁻6 हर्ट्ज. तो लैम्डा हो जाएगा 1.7 गुना 10⁻3 बाई 4.2 गुना 10⁻6 यानी 4 गुना 10⁻⁻4 मीटर. अब यहाँ से अगर निकालेंगे तो आंसर आएगा ऑप्शन ए 4 गुना 10⁻⁻4 मीटर. फिर है कि द टू वेव आर सेड टू बी कोहेरेंट. कब? जब उसका फ्रीक्वेंसी सेम होगा, फेज और एम्पलीट्यूड भी क्या हो जाएगा? सेम हो जाएगा. तो टू वेव आर सेड टू बी कोहेरेंट देन दे हैव द सेम फ्रीक्वेंसी एम्पलीट्यूड एंड द कांस्टेंट फेज डिफरेंस. नेक्स्ट है फ्रॉम अ वेव इक्वेशन y इक्वल टू 0.5 फाइंड 2 पाई बाई 3.2 64 t माइनस x. फ्रीक्वेंसी ऑफ द वेव कितना हो जाएगा? तो स्टैंडर्ड इक्वेशन ऑफ प्लेन प्रोग्रेसिव हार्मोनिक वेव है y इक्वल टू ए फाइंड 2 पाई बाई लैम्डा vt माइनस x. तो गिवन इक्वेशन हो जाएगा y इक्वल टू 0.5 फाइंड 2 पाई बाई 32 54 t माइनस x. तो यहाँ से फ्रीक्वेंसी निकालेंगे तो आ जाएगा कितना? 20 हर्ट्ज. तो आंसर इसका जाएगा ऑप्शन सी 20 हर्ट्ज. फिर आता है कि सी एफ विद द वेलोसिटी ऑफ द साउंड इन द एयर देन सी विद द आरएमएस वेलोसिटी. तो वेलोसिटी ऑफ साउंड सी एफ इज इक्वल टू होता है सी एफ इक्वल टू होता है गामा पी बाई रो where P the pressure, F is the density and gamma is the atomicity of the gas or ratio of the Cp and Cb. तो RMS velocity of the gas molecule given by C is equal to root over 3 P by rho. तो C पर C हो जाएगा C is equal to C into root over gamma by 3. तो आंसर कितना जाएगा? आंसर जाएगा ऑप्शन C C is equal to C root over gamma by 3. फिर आता है कि which of the following equation represents a wave. तो ए फन ओमेगा टी माइनस के एक्स जो होता है ये वेव को रिप्रेजेंट करता है. तो बाई इक्वल टू ए फन ओमेगा टी माइनस एक्स ये है जो वेव हो गया. Other forms of the wave equation are y equal to f1 omega t minus kx and y equal to f1 k vt minus x हो जाएगा. आंसर कितना जाएगा? ऑप्शन डी. नेक्स्ट है द फ्रीक्वेंसी ऑफ द सिनुसॉइडल वेव 0.4 cos 2000 t प्लस 0.8 वुड बी. तो इक्वेशन ऑफ द हार्मोनिक वेव इन द कोसाइन फंक्शन y equal to a cos 2 pi वी टी प्लस फाइव, तो गिवन इक्वेशन हो जाएगा 0.4 कॉफ 2000 टी प्लस 0.8। कंपेयर करेंगे इक्वेशन को तो 2 पाई वी इक्वल टू 2000, तो वी इक्वल टू हो जाएगा यानी म्यू इक्वल टू हो जाएगा 2000 बाई 2 पाई यानी कि 1000 बाई पाई हर्ट्ज। तो आंसर आएगा ऑप्शन डी 1000 बाई पाई हर्ट्ज। फिर आता है with the propagation of a longitudinal wave through a material density, the quantity transmitted in the propagation direction कितना r, तो in the longitudinal wave energy is propagated along with the wave motion without any net transport of the mass of the medium। तो आंसर कौन सा आएगा? आंसर आएगा ऑप्शन बी एनर्जी। फिर आता है कि the transverse wave represented by the equation y equal to 4 sin pi by 6 sin 3x minus 15 th। तो स्टैंडर्ड इक्वेशन ऑफ द ट्रांसवर्स वेव इज y इक्वल टू a sin 2 pi t by t minus 2 pi x by lambda। तो y इक्वल टू 4 sin pi by 6 sin 15 t minus 3x, तो 2 pi by lambda इक्वल टू 3, तो lambda इक्वल टू 2 pi by 3 यानी 2 pi by t इक्वल टू 15, तो t इक्वल टू हो जाएगा 2 pi by 15। तो v इक्वल टू हो जाएगा lambda by t यानी 2 pi by 3 by 2 pi by 15 यानी कितना आ जाएगा 5। तो आंसर आएगा इसका आंसर ऑप्शन सी कि स्पीड ऑफ द प्रोपेगेशन हो जाएगा 5। फिर आता है कि वेलोसिटी ऑफ द साउंड वेव इन द एयर इज 330 मीटर पर सेकंड फॉर ए पर्टिकुलर साउंड वेव इन द एयर, पाथ डिफरेंस ऑफ द 40 सेंटीमीटर इज इक्वल टू द फेज डिफरेंस ऑफ 1.6 पाई। तो फ्रीक्वेंसी कितना हो जाएगा? तो एट द गिवन टाइम टी बराबर कांस्टेंट, द फेज चेंजेस विद द एक पोजीशन x, द फेज चेंजेस डेल्टा पाई एट टाइम एट गिवन टाइम फॉर एच वेवलेंथ लैम्डा फॉर डिफरेंस डेल्टा एक्स गिवन बाय डेल्टा फाई इक्वल टू 2 पाई बाय लैम्डा इनटू डेल्टा एक्स, और डेल्टा एक्स इक्वल टू हो जाएगा लैम्डा बाई 2 पाई। तो डेल्टा पाई और लैम्डा इक्वल टू 2 पाई बाय लैम्डा एक्स इंटू डेल्टा फाई, तो डेल्टा एक्स इक्वल टू होगा 0.4 मीटर और डेल्टा फाई हो जाएगा 1.6 पाई। तो लैम्डा इक्वल टू होगा 2 पाई गुना 0.4 बाई 1.6 पाई यानी कि 0.5 मीटर। हम इसका आगे करें तो फ्रीक्वेंसी ऑफ द वेव हो जाएगा म्यू इक्वल टू वी बाई लैम्डा यानी 330 बाई 0.5 यानी 660 हर्ट्ज। तो भी हो जाएगा 330 मीटर पर सेकंड जो कि हो जाएगा वेलोसिटी ऑफ द साउंड। तो आंसर कितना जाएगा? ऑप्शन सी 660 हर्ट्ज है जो इसका आंसर चल जाएगा। अगला क्वेश्चन है कि 5.5 meter length of the string has a 0.035 kg. If the tension in the string is 77 न्यूटन, the speed of the wave on the string कितना हो जाएगा? तो हम जानते हैं कि v इक्वल टू होता है रूट ओवर टी बाई म्यू, तो म्यू हो जाएगा 0.035 बाई 5.5, तो टी हो जाएगा 77 न्यूटन। तो यहाँ से वैल्यू पुट करेंगे 77 बाई 0.035 गुना 5.5, तो कितना आ जाएगा 110 मीटर पर सेकंड। तो इसका आंसर आएगा ऑप्शन ए 110 मीटर पर सेकंड। फिर आता है कि द एम्पलीट्यूड ऑफ द साउंड इज डबल एंड द फ्रीक्वेंसी रिड्यूस्ड टू 1/4, द इंटेंसिटी ऑफ द साउंड एट द सेम पॉइंट पर कितना हो जाएगा? तो फैक्टर फ्रॉम विच द इंटेंसिटी डिपेंड्स फॉर द एम्पलीट्यूड ऑफ द वाइब्रेशन ऑफ द साउंड आई डायरेक्टली प्रोपोर्शनल टू ए स्क्वायर, surface area of the vibrating sound I directly proportional to A, density of the medium I directly proportional to rho, or frequency of the source I directly proportional to B square. The motion of the medium which change effectively velocity B of the and the I directly proportional B I directly proportional to A square or I directly proportional to B square. तो इंटेंसिटी becomes 2 square by 4 square equal to 1 by 4। तो इसका कितना जाएगा? ऑप्शन सी डिक्रीज बाय फैक्टर ऑफ द 4। फिर आता है द वेलोसिटी ऑफ द साउंड इन एनी गैस डिपेंड्स अपॉन द The velocity of sound in the gas depends upon the B, the answer is option B, density of the density and the elasticity of the gas पर depend करता है। तो from the purely theoretical consideration Newton came to be conclusion that ठीक है velocity of the longitudinal wave through the any medium solid liquid or gas depends upon the elasticity and density of the medium। Newton gave the formula V equal to root over E by rho, जहाँ V जो है velocity of the sound in the medium है, E जो है coefficient of the elasticity in the medium है, rho जो है density of the undisturbed medium है। फिर आता है इक्वेशन ऑफ द प्रोग्रेसिव वेव गिवन बाय y इक्वल टू 4 sin x t by 5 minus x by 9 plus pi by 6। तो which of the following is correct? Equation of the plane progressive simple wave is y equal to a sin 2 pi t by t minus x by lambda plus pi। तो given equation is y equal to 4 sin x by t by 5 minus x by 9 plus pi by 6 multiplying and dividing x by t minus x by lambda by 2, it is written as y equal to 4 sin 2 pi t by 10 minus x by 18 plus pi by 6। तो a को वैल्यू रखेंगे 4, टी को 10 और लैम्डा को 18, तो 5 इक्वल टू हो जाएगा पाई बाई 6। तो ऑप्शन कौन सा हो जाएगा? ऑप्शन बी है जो करेक्ट हो जाएगा, यानी कि लैम्डा इक्वल टू आ जाएगा 18 सेंटीमीटर। नेक्स्ट है कि द लेंथ ऑफ द स्ट्रिंग ऑफ ए म्यूजिकल इंस्ट्रूमेंट इज 90 सेंटीमीटर एंड हैज ए फंडामेंटल फ्रीक्वेंसी ऑफ द 120 हर्ट्ज। Therefore be the preferred, therefore did we prefer to produce the fundamental frequency of the 140 hertz। तो लेंथ ऑफ द स्ट्रिंग ऑफ द म्यूजिकल इंस्ट्रूमेंट जो है L बराबर 90 सेंटीमीटर यानी 0.9 मीटर। फंडामेंटल फ्रीक्वेंसी F1 इक्वल टू 120 पर दिया हुआ है यानी F2 इक्वल टू 140 हर्ट्ज। तो हम जानते हैं कि F जो होता है 1 बाई आई होता है, तो F1 बाई F2 हो जाएगा I2 बाई I1। तो एफ जो होता है 1/L होता है, तो F1/F2 हो जाएगा L2/L1, यानी F2 इक्वल टू हो जाएगा F1L1/F2, यानी क्या आ जाएगा 120 गुना 0.9/4, यानी कि 2/3 गुना 0.9, यानी कितना आ जाएगा 50 सेंटीमीटर। तो इसका आंसर होगा ऑप्शन बी 50 सेंटीमीटर। फिर आता है कि in a guitar, two of strings A and B made of the same material are slightly out of the tune and produce beats of the frequency 6 Hz. When tension in the beat slightly decrease, the beat frequency increases to 5 Hz. If the frequency of A is 530 Hz, the original frequency of B कितना हो जाएगा? तो in the case of the beats from one unknown frequency, VB is equal to VA plus minus beats, तो VA is equal to 540 Hz and the 6 Hz. BB is equal to 530 plus minus 6 यानी 536 Hz और 524 Hz. When the tension in the beat is slightly increased, then the beat frequency increases to the 5 Hz. This is possible if we take the original frequency of B as 524 Hz. तो करेक्ट ऑप्शन जाएगा ऑप्शन ए 524 Hz. नेक्स्ट है कि a tuning fork with frequency 800 Hz produces reonins in a reonins column tube with upper end open and the lower end closed by a butter surface. Successive reonins are observed at a length of 9.15 cm, 31.25 cm and 52.15 cm. तो स्पीड ऑफ द साउंड इन द एयर है जो कितना हो जाएगा? तो यहाँ पर अगर देखें तो L1 इजिकल टू λ/4 हो जाएगा और L2 इजिकल टू λ/4 प्लस λ/2 यानी 3 λ/4 हो जाएगा। तो L2 माइनस L1 हो जाएगा 3 λ/4 माइनस λ/4 इजिकल टू हो जाएगा λ/2। तो लैम्डा इजिकल टू हो जाएगा 2L1 माइनस L2 यानी कि 2f L2 माइनस L1 और लैम्डा इजिकल टू हो जाएगा V/F। तो पुटिंग द वैल्यू f इजिकल टू 800 हर्ट्ज, L1 इजिकल टू 9.15 सेंटीमीटर, L2 इजिकल टू 31.25 सेंटीमीटर। तो V इजिकल टू 2 गुना 800 यानी 31.25 माइनस 9.15, तो कितना आ जाएगा 340 मीटर पर सेकंड। तो इसका आंसर कितना आ जाएगा? इसका आंसर आएगा ऑप्शन सी 340 मीटर पर सेकंड। फिर आता है द फंडामेंटल फ्रीक्वेंसी इन एन ऑर्गन पाइप इज इक्वल टू द थर्ड हार्मोनिक ऑफ ए क्लोज्ड ऑर्गन पाइप इफ द लेंथ ऑफ द क्लोज्ड ऑर्गन पाइप इज 20 सेंटीमीटर, द लेंथ ऑफ द ओपन ऑर्गन पाइप कितना हो जाएगा? तो F1 इज इक्वल टू V/12, F डैश इक्वल टू 3B/4L डैश। तो F इक्वल टू F डैश यानी V/12 इक्वल टू 3B/4L डैश। तो L इक्वल टू हो जाएगा 2/3L डैश। तो L डैश इक्वल टू हो जाएगा 20 सेंटीमीटर। तो L इक्वल टू हो जाएगा 2/3 गुना 20 यानी क्या आ जाएगा 13.3 सेंटीमीटर। तो 13.3 सेंटीमीटर इसका जो आंसर आएगा। फिर है कि ट्यूनिंग फॉर्क यू टू प्रोड्यूस reonins in a glass tube. The length of the air column in this tube can be adjusted by a variable piston. At room temperature of 27 degrees Celsius, two successive reonins are produced at 20 cm and 23 cm of the column length. If the frequency of the tuning port is 320 Hz, then the velocity of the sound in the air at 45 degrees Celsius पर कितना हो जाएगा? तो at for the first reonins L1 is equal to λ/4, for the second reonins L2 is equal to 3 λ/4. तो L2 माइनस L1 हो जाएगा 3 λ/4 माइनस λ/4, तो लैम्डा इक्वल टू होगा 2 L2 माइनस L1 एंड द वेलोसिटी ऑफ द साउंड भी गिवन बाय v इक्वल टू म्यू लैम्डा। तो म्यू इधर फ्रीक्वेंसी है तो v इक्वल टू हो जाएगा v 2 L2 माइनस L1। अब वैल्यू को रखेंगे 2 320 0.13 माइनस 0.20 यानी 2 गुना 320 गुना 0.53 तो आएगा 339.2 यानी कि लगभग 339 मीटर पर सेकंड। तो आंसर इसका जाएगा ऑप्शन बी 339 मीटर पर सेकंड। नेक्स्ट है कि two nearest harmonics of a tube closed at one end and open at another end are the 4 Hz and the 5 Hz. तो what is the fundamental frequency of the system? तो हम जानते हैं कि frequency of the nth harmonic in a closed tube में होता है f equal to 2n-1/v into 4l जहाँ n 1 2 3 है। Now give then the two nearest harmonics are given as the 4 Hz and the 5 Hz. 2n-1/v/4l equal to the 4 Hz और नेक्स्ट हार्मोनिक हो जाएगा 2n प्लस 1 v/4l इक्वल टू 4 है। तो सब्ट्रैक्ट करेंगे इक्वेशन 1 की इक्वेशन 2 से बी गेट 2n माइनस 1 माइनस 2n माइनस 1 v/4l इक्वल टू 4 माइनस 220। तो 2 इंटू v/4l इक्वल टू 40 तो v/4l इक्वल टू कितना आ जाएगा 20 हर्ट्ज। तो इसका आंसर ऑप्शन बी 20 हर्ट्ज। फिर आता है कि the second overtone of an open organ pipe has the same frequency as the first overtone of the closed pipe L meter long. The length of the open pipe कितना हो जाएगा? तो bn इक्वल टू n/12 जहाँ n 1 2 3 है। For the second overtone n is equal to 3 और v2 is equal to 3v/12 जहाँ l जो है लेंथ ऑफ द ओपन ऑर्गन पाइप है। तो फॉर क्लोज्ड ऑर्गन पाइप vn is equal to 12 plus 1 2n plus 1 by 4l into v where n बराबर 0 1 2 3 है। तो फर्स्ट overtone for the closed organ pipe n is equal to 1 तो v1 से equal to 3v/4l और v2 0 equal to v1 से equal to 3v/12 यानी कि 3v/4l। तो l1 इक्वल टू कितना हो जाएगा 12। तो इसका आंसर आएगा ऑप्शन बी l1 इक्वल टू 12। नेक्स्ट है कि 3 साउंड वेव ऑफ द इक्वल एम्पलीट्यूड हैव द फ्रीक्वेंसी n-1 n और n+1 दे सुपर इम्पोज टू गिव द बीट्स द नंबर ऑफ द बीट्स प्रोड्यूस्ड पर सेकंड कितना हो जाएगा? तो हम जानते हैं कि बीट फ्रीक्वेंसी f1 f2 इक्वल टू होता है n-n-1 इक्वल टू 1 एंड सिमिलरली फॉर n and n+1 बीट फ्रीक्वेंसी n+1 n इक्वल टू होता है 1। तो आंसर आएगा ऑप्शन ए 1 आ जाएगा। फिर आता है कि द फंडामेंटल फ्रीक्वेंसी ऑफ ए क्लोज्ड ऑर्गन पाइप ऑफ द लेंथ 20 cm is equal to the second overtone of the organ pipe at both the ends. The length of the organ pipe opens at both ends. So the fundamental frequency of a closed and open organ pipe are given as Vc equal to V by 4L and Vy equal to V by 2L dash. So given the second overtone, that means the third harmonics of the open pipe is equal to the fundamental frequency of the closed pipe. So 3 V naught is equal to Vc. तो 3 इंटू V बाई 2L dash is equal to V by 4L. तो L dash is equal to कितना आ जाएगा 120 सेंटीमीटर। तो इसका आंसर कितना आ जाएगा ऑप्शन सी 120 सेंटीमीटर। फिर आता है कि an air column closed at one end and open at other end reunite with a tuning fork when the smallest length of the column is 50 cm. The next larger length of the column reuniting with the same tuning fork कितना हो जाएगा तो L मिनिमम इक्वल टू दिया लैम्डा बाई 4 तो 50 सेंटीमीटर इक्वल टू लैम्डा बाई 4 तो लैम्डा इक्वल टू आ जाएगा 200 सेंटीमीटर तो L इक्वल टू आ जाएगा लैम्डा बाई 4 प्लस लैम्डा बाई 2 यानी 3 लैम्डा बाई 4 तो यहाँ पे कितना आ जाएगा 150 सेंटीमीटर। तो आंसर आएगा ऑप्शन बी 150 सेंटीमीटर। नेक्स्ट है if string is of stretcher between fixed points separated by the 25 cm, it is observed that to have the reunion frequency of 420 Hz and 315 Hz. There are no other reunion frequency between these two. The lowest reunion frequency for the two string कितना हो जाएगा तो L बराबर 75 cm, F1 बराबर 420 Hz, F2 बराबर 315 Hz. And the two consecutive reunion frequency for a string fixed at both ends will be तो यहाँ से निकालेंगे तो F1 इक्वल टू एन वी बाई 12, F2 इक्वल टू एन प्लस वन वी बाई 12। F2 माइनस F1 इक्वल टू होगा 420 माइनस 315 यानी n प्लस वन वी बाई 12 माइनस एन वी बाई 12 इक्वल टू आएगा 105 हर्ट्ज। तो वी बाई 12 इक्वल टू आएगा 105 हर्ट्ज। तो लोएस्ट रिजोनेंस फ्रीक्वेंसी ऑफ द स्ट्रिंग कितना आएगा 105 हर्ट्ज। तो इसका आंसर आएगा ऑप्शन डी 105 हर्ट्ज। फिर आता है कि इफ n1 n2 and n3 are the fundamental frequency of the three segment into which a string is divided, then the original fundamental frequency n of the string कितना हो जाएगा तो हम जानते हैं कि फॉर द फर्स्ट पार्ट n1 इज इक्वल टू वी बाई 2l1 तो l1 इज इक्वल टू हो जाएगा वी बाई 2n1। फॉर द सेकंड पार्ट n2 इज इक्वल टू वी बाई 2l2 तो l2 इज इक्वल टू हो जाएगा वी बाई 2n2। और फॉर द थर्ड पार्ट n3 इज इक्वल टू वी बाई 2l3 तो l3 इज इक्वल टू हो जाएगा वी बाई 2n3। फॉर द कंप्लीट बार n इज इक्वल टू वी बाई 12 तो l इज इक्वल टू हो जाएगा वी बाई 2n। फॉर वी हैव l इज इक्वल टू l1 प्लस l2 प्लस l3 तो वी बाई 2n इज इक्वल टू वी बाई n1 प्लस वी बाई 2n2 प्लस वी बाई 3n3। तो 1 बाई n इक्वल टू हो जाएगा 1 बाई n1 प्लस 1 बाई n2 प्लस 1 बाई n3 यानी इसका आंसर क्या जाएगा ऑप्शन ए 1 बाई n इक्वल टू 1 बाई n1 प्लस 1 बाई n2 प्लस 1 बाई n3। फिर आता है नंबर ऑफ द पॉसिबल नेचुरल ऑसिलेशन ऑफ द एयर कॉलम इन अ पाइप क्लोज्ड एट वन एंड ऑफ लेंथ 85 सेंटीमीटर व्हिच फ्रीक्वेंसी लाई बिलो 1250 हर्ट्ज। तो फॉर द पाइप क्लोज्ड एट वन एंड Fn is equal to n v by 4l यानी कि n is into 4। Here n is odd number for the given condition n can go up to n is equal to 11, n is equal to 1, 3, 5, 7, 9 और 11। So number of the possible natural oscillation could be fixed which are below 1250 हर्ट्ज। तो आंसर कितना जाएगा ऑप्शन डी यानी कि आ जाएगा ऑप्शन 6 है जो इसमें 6 आना चाहिए। फिर आता है कि if we study the vibration of a pipe open at both ends which of the following statement is not true। तो ऑप्शन डी प्रेफर चेंज विल बी मैक्सिमम एट बोथ एंड ऐसा नहीं होता है। स्टेटमेंट इज नॉट ट्रू बिकॉज एट दी ओपन एंड प्रेफर चेंज है जो कितना होता है 0 होता है। तो ओपन एंड में भी एंटी नॉट सही है। ऑल हार्मोनिक्स ऑफ द फंडामेंटल फ्रीक्वेंसी ऑफ विल बी जनरेटेड ये भी सही है। ऑल हार्मोनिक्स ऑफ द फंडामेंटल फ्रीक्वेंसी विल जनरेटेड ये भी सही है। नेक्स्ट है कि फोर्स ऑफ द अननोन फ्रीक्वेंसी गिव 4 बिट्स when founded with a force of the known frequency per high watt. The second harmonic of the force of the unknown frequency gives the 5 beats per second when founded with a force of the frequency 513 हर्ट्ज। The unknown frequency कितना हो जाएगा तो 200 और 250 254 508 और 250 240 492। तो यहाँ पे करेंगे तो कितना आ रहा है 5 बिट्स के बाद 513 21 बिट्स के बाद 21 बिट ना। तो अननोन फ्रीक्वेंसी कितना हो जाएगा 254। तो इसका आंसर होगा ऑप्शन ए 254 हर्ट्ज। फिर आता है when the string is divided into three segments of the length I1, I2 and I3, the fundamental frequency of these three segments are mu1, mu2 and mu3 respectively. The ordinary fundamental frequency of the string कितना हो जाएगा तो the fundamental frequency of the string mu is equal to 1 by 12 root over t by m। तो mu1 L1 is equal to mu2 L2 is equal to mu3 L3 is equal to k। तो L1 is equal to k by v1, L2 is equal to k by v2 और L3 is equal to k by v3। तो ऑरिजिनल लेंथ L इक्वल टू के वाई भी आ जाएगा। तो L इज इक्वल टू L1 प्लस L2 प्लस L3 तो के वाई V1 इज इक्वल टू के वाई म्यू इक्वल टू के वाई V1 प्लस के वाई V2 प्लस के वाई V3। तो 1 बाई म्यू इक्वल टू 1 बाई V1 प्लस 1 बाई म्यू2 प्लस 1 बाई V3। तो आंसर आएगा ऑप्शन सी 1 बाई म्यू इक्वल टू 1 बाई V1 प्लस 1 बाई V2 प्लस 1 बाई म्यू3। Next, two sources of the font placed close to each other are emitting progressive waves given by the y1 equal to 4 fan 6 pi t and y2 equal to 5 fan 6 pi t and observer located near the two force one be here. तो बाई वन इक्वल टू 4 फाइन 6 फॉर पाई टी, बाई टू इक्वल टू 5 फाइन 6 फॉर 8 पाई टी. तो बाई इक्वल टू एफ वन तो पाई एफ टी, एफ वन इक्वल टू 3 फॉर हर्ट, एफ टू इक्वल टू 4 हर्ट. तो नंबर ऑफ बिट्स एफ टू माइनस एफ वन इक्वल टू हो जाएगा 4 सेकंड. तो बिना आई मैक्स बाई में हो जाएगा ए वन प्लस ए टू बाई ए वन माइनस ए टू का होल स्क्वायर यानी 4 प्लस 5 बाई 4 माइनस 5 का होल स्क्वायर यानी कितना आ जाएगा 81. तो आंसर होगा फंडी 4 बिट्स विद इंटेंसिटी ऑफ 81:1 बिटवीन द वैक्सिंग एंड द बैनिंग. फिर आता है कि ट्यूनिंग फॉर्क A tuning fork of the frequency 512 Hz makes 4 beats per second with vibrating string of the piano. The beats frequency decreases to 2 beats per second when the tension in the piano of string is slightly increased. The frequency of the piano string before increasing the tension pitch. तो let NP with the frequency of the piano as NP directly proportional to root T. तो NT जो है frequency of the tuning fork हो जाएगा 512 Hz, X जो है beats frequency हो जाएगा 4 beats per second. which is decreasing तो 400 हो जाएगा 2. तो changing the tension in the piano bar, also tension of the piano bar increasing, so NP बढ़ेगा. तो NP ग्रेटर और बढ़ेगा माइनस एन एफ इक्वल टू एक्स, तो रॉन्ग. तो एन एफ माइनस एन पी जगह बढ़ेगा तो एक्स घटेगा, तो ये है जो करेक्ट है. तो एन पी जो होगा इक्वल टू एन पी माइनस एन एफ माइनस एक्स इक्वल टू 512 माइनस 4 इक्वल टू 508 हर्ट्ज. आंसर कितना जाएगा ऑप्शन डी 508 हर्ट्ज. फिर आता है कि two periodic waves of the intensity I1 and I2 pass through a region at the same time in the same direction. The sum of the maximum and the minimum intensity कितना हो जाएगा. तो the intensity of the direction proportional to the square of the amplitude I directly proportional to a square. So for the maximum intensity given by I max equal to root over I1 plus root over I2 के square. I1 और I2 intensity of two waves है. तो I min equal to हो जाएगा root over I1 minus root over I2 के whole square. तो I max plus I min equal to हो जाएगा 2 root I1 plus I2 यानी कि आ जाएगा आंसर D. फिर आता है कि two sounds of the wave with wavelength 5 meter and 5.5 meter respectively, each propagating the gaps with velocity 330 meter per second. We expect the following number of the beats per second. तो V1 is equal to 5.0 meter, beat is equal to 330 meter per second, and lambda 2 equal to 5.5 meter. The relation between the frequency and the wavelength of is given by, तो V is equal to N lambda और N is equal to V by lambda. तो अगर यहाँ से निकालें तो द फ्रीक्वेंसी corresponding to the wavelength lambda 1 equal to N1 equal to V by lambda 1 यानी 330/5 यानी 66 हर्ट्ज. तो द फ्रीक्वेंसी corresponding to the lambda 2 N2 equal to V by lambda 2 यानी 330/5.5 यानी 60 हर्ट्ज. तो नंबर ऑफ द बीट्स पर सेकंड हो जाएगा N1 माइनस N2 इक्वल टू 66 माइनस 60 इक्वल टू कितना आ जाएगा 6. तो आंसर इसका जाएगा ऑप्शन डी 6. नेक्स्ट है इफ टू वाइब्रेटिंग ट्यूनिंग फॉर्क्स प्रोड्यूस प्रोग्रेसिव वेव गिवन बाय द बाई वन इक्वल टू 4 फाइन 500 पाई टी एंड बाई टू इक्वल टू 2 फाइन 506 पाई टी. तो नंबर ऑफ द बीट्स प्रोड्यूस्ड पर मिनट कितना हो जाएगा. तो बाई वन इक्वल टू 4 फाइन 500 पाई टी, बाई टू इक्वल टू 2 फाइन 506 पाई टी. हम जानते हैं कि बाई इक्वल टू होता है ए फाइन ओमेगा टी, तो ओमेगा इक्वल टू होता है 500 पाई. तो एन वन इक्वल टू होता है 500 पाई बाई 2 पाई यानी 250 बीट्स पर सेकंड, और ओमेगा टी इक्वल टू हो जाएगा 506 पाई. तो एन टू इक्वल टू हो जाएगा 506 बाई 2 पाई यानी 253 बीट्स पर सेकंड. तब से नंबर ऑफ द बीट्स प्रोड्यूस हुई एन टू माइनस वन इक्वल टू 253 माइनस 250 यानी 3 बीट्स पर सेकंड. तो 3 गुना 60 यानी कि 180 बीट्स पर मिनट. If the equation of the wave is given and to find the physical quantity like the amplitude, wavelength, time period, frequency, just compare the given equation with the standard equations of the wave. इसका आंसर कितना जाएगा ऑप्शन बी 180. फिर आता है कि इक्वेशंस ऑफ द टू प्रोग्रेसिव वेव्स आर गिवन बाय y1 equal to f omega t plus phi 1 and y2 equal to f omega t plus phi 2. If the amplitude and time period of the resultant wave are same as that of the both the waves, then phi 1 minus phi 2 कितना हो जाएगा. तो गिवन प्रोग्रेसिव वेव आर y1 equal to f omega t plus phi 1 और y2 equal to f omega t plus phi 2. तो रिजल्टेंट ऑफ द टू वेव हो जाएगा y equal to y1 plus phi 2 और a equal to हो जाएगा phi omega t plus phi 1 plus phi omega t plus phi 2. If a is the amplitude of the resultant wave, then a is equal to a और a square equal to a square plus a square plus 2a square cos phi और a square equal to a square plus a square plus 2a square cos phi. तो cos phi equal to minus 1/2 यानी cos 1/20 और phi equal to हो जाएगा 120 डिग्री यानी 2π/3. तो phi 1 minus phi 2 हो जाएगा 2π/3. तो आंसर कितना आ जाएगा ऑप्शन बी 2π/3. फिर आता है कि फोनोमीटर वायर when vibrated in the full length has a frequency n. Now it is divided with the help of the bridges into a number of the segment of the length L1, L2, L3. When vibrated, these segment have the frequency N1, N2, N3. Then the correct relation क्या हो जाएगा. तो from the law of the length, the frequency of the vibrating string is inversely proportional to its length. N जो है inversely proportional to length आएगा. तो NL is equal to constant. तो N into L is equal to K. तो for the segment of the string of the length L1, L2, L3 and frequency N1, N2, N3, total length of the string is L. तो L इज इक्वल टू L1 प्लस L2 प्लस L3 यानी के बाई एन इज इक्वल टू के बाई N1 प्लस के बाई N2 प्लस के बाई N3। तो 1 बाई एन इज इक्वल टू 1 बाई N1 प्लस 1 बाई N2 प्लस 1 बाई N3। इसका आंसर है ऑप्शन सी कि 1 बाई एन इज इक्वल टू 1 बाई N1 प्लस 1 बाई N2 प्लस 1 बाई N3। फिर आता है कि टू फोर्स आर एट डिफाइनाइट डिस्टेंस अपार्ट, दे इमिट साउंड्स ऑफ द वेवलेंथ लैम्डा, एन ऑब्जर्वर situated between them on land joining approaches one force with the speed u, then the speed of the boat heard a sound second by the observer will be। तो जानते हैं कि v be the speed of the sound and n be the original frequency of the each force। They emit sound of the wavelength lambda when the observer moves towards the one force say a, the apparent frequency of a as observed by the observer will be n f equal to n b plus u by b, जहाँ u जो है स्पीड ऑफ द साउंड टॉर्ड्स ए है द ऑब्जर्वर इन ऑफ रिसीविंग force b, for the apparent frequency of the b observed will be n double dash equal to n b minus u by b if u जो है speed of the observer going away from b है। thus the number of the bits हो जाएगा x equal to n dash minus n double dash, तो n equal to n b plus u minus by b minus b minus u by b, तो n by b equal to b plus u minus b plus u यानी 2 nu by b और b इक्वल टू हो जाएगा एन लैम्डा, तो एक्स इक्वल टू हो जाएगा 2u बाई लैम्डा। तो आंसर कितना जाएगा ऑप्शन ए 2u बाई लैम्डा। फिर आता है कि टू वेव ऑफ द वेवलेंथ 50 सेंटीमीटर एंड 51 सेंटीमीटर प्रोड्यूस 12 बीट्स पर सेकंड। द स्पीड ऑफ द साउंड कितना हो जाएगा, तो बीट्स प्रोड्यूस ड्यू टू द टू फ्रीक्वेंसी इज गिवन बाय n1 माइनस n2 वेयर n1 एंड n2 आर द फ्रीक्वेंसी ऑफ द टू वेव्स। तो नंबर ऑफ बीट्स हो जाएगा 12 सेकंड। तो एन लैम्डा 1 इक्वल टू हो जाएगा 50 सेंटीमीटर यानी 0.5 मीटर और लैम्डा 2 इक्वल टू 51 सेंटीमीटर यानी 0.51 सेंटीमीटर। तो n1 माइनस n2 हो जाएगा 12, तो v बाई लैम्डा 1 माइनस v बाई लैम्डा 2 इक्वल टू हो जाएगा 12। तो v इंटू लैम्डा 2 माइनस लैम्डा 1 बाई लैम्डा 1 इंटू लैम्डा 2 इक्वल टू 12, तो v इक्वल टू हो जाएगा 12 लैम्डा 1 लैम्डा 2 बाई लैम्डा 2 माइनस लैम्डा 1। तो आंसर ऑप्शन, अब इसको वैल्यू अगर रख दें सिंपली तो 12 गुना 0.50 गुना 0.51 बाई 0.51 माइनस 0.50, तो कितना आ जाएगा 306 मीटर पर सेकंड। तो स्पीड ऑफ साउंड कितना आ जाएगा 306 मीटर पर सेकंड। तो आंसर हो जाएगा इसका ऑप्शन है 306 मीटर पर सेकंड। Next take a standing wave having 3 node and 2 antinode is formed between two atoms having distance of 1.21 angstrom between them। तो wavelength of the standing wave कितना हो जाएगा, तो given of standing wave is shown in the figure node antinode node antinode node and length of the one loop of the segment is lambda by 2, so length of the two segment is 2 lambda by 2। so according to the question 2 lambda by 2 is equal to 1.21 angstrom, तो lambda is equal to 1.21 angstrom। तो आंसर ऑप्शन है 1.21 angstrom। फिर आता है कि a cylindrical free-on tube open at both ends has a fundamental frequency f in the air if half of the length is dipped vertically in the water, the fundamental frequency of the air column कितना हो जाएगा, तो हम जानते हैं f equal to होता है v by 12। when half length of the tube is dipped vertically in the water then the length of the air column becomes half यानी I def equal to L by 2 and the pipe becomes closed। so the new fundamental frequency of the closed pipe f def equal to v by 4 L def यानी v by 4 L by 2 and v by 2L। From the equation 1 and 2 we get f def equal to f, hence there will be no change in the fundamental frequency। तो यहाँ पर क्या रहेगा आंसर, आंसर रहेगा ऑप्शन सी एफ ही रह जाएगा। फिर आता है कि पल्स ऑफ द वेव travels along the stretched string and reach the fixed end of the string, it will be reflected back with the pulse of the wave when travels along the stretched string and reach the fixed end of the string, then it will be reflected back to the same medium and the reflected rays of a phase of pi with the incident wave and the wave velocity after reflection will reverse। तो आंसर ऑप्शन है कि फेज एंगल ऑफ 180 डिग्री विद द वेलोसिटी क्या हो जाएगा, रिवर्स्ड हो जाएगा। नेक्स्ट है कि स्टैंडिंग वेव फॉर प्रोड्यूस्ड इन द 10 मीटर लॉन्ग स्ट्रेचेड स्ट्रिंग इफ द स्ट्रिंग वाइब्रेट्स इन द 5 सेगमेंट एंड द वेव वेलोसिटी 20 मीटर पर सेकंड, द फ्रीक्वेंसी कितना हो जाएगा, तो इन द केस ऑफ द स्टैंडिंग वेव द लेंथ ऑफ द वन सेगमेंट इज लैम्डा बाय 2, देयर आर 5 सेगमेंट इन टोटल लेंथ ऑफ द स्ट्रिंग इज 10 मीटर, तो 5 लैम्डा बाय 2 इक्वल टू 10, तो लैम्डा इक्वल टू 4 मीटर। फ्रीक्वेंसी हो जाएगा एन इक्वल टू वी बाई लैम्डा यानी वी फाई 4 इक्वल टू 5 हर्ट्ज, तो वी इक्वल टू कितना 20 मीटर पर सेकंड। तो स्टैंडिंग वेव इज एग्जांपल ऑफ द इंटरफेरेंस, डिस्ट्रक्टिव इंटरफेरेंस मींस नोड एंड कंस्ट्रक्टिव इंटरफेरेंस मींस एंटी नोड। तो आंसर है ऑप्शन बी 5 हर्ट्ज। फिर आता है टू वेव ऑफ द सेम फ्रीक्वेंसी एंड इंटेंसिटी सुपर इम्पोज ऑन ईच अदर इन द अपोजिट फेजेज, आफ्टर द सुपर इम्पोजिशन द इंटेंसिटी एंड फ्रीक्वेंसी ऑफ द वेव क्या हो जाएगा, तो interference phenomena is common to the sound and the light। In sound, the interference is said to be constructive at the point where the resultant intensity maximum are in the phase and the destructive at the point where the resultant intensity minimum or zero are in the opposite phase। तो इसका आंसर क्या जाएगा, आंसर है ऑप्शन डी बिकम 0। नेक्स्ट है कि टू वेव्स आर अप्रोचिंग ईच अदर विद वेलोसिटी ऑफ 20 मीटर पर सेकंड एंड फ्रीक्वेंसी एन, द डिस्टेंस कितना हो जाएगा, तो डिस्टेंस बिटवीन टू सक्सेसिव नोड इज इक्वल टू होता है लैम्डा बाय 2, बट वी नो दैट वी इज इक्वल टू म्यू लैम्डा, तो लैम्डा बाय 2 इक्वल टू हो जाएगा वी बाई 2 म्यू, v by 2 mu, तो v is equal to 20 मीटर पर सेकंड, और v is equal mu is equal to हो जाएगा n, तो लैम्डा बाई 2 इक्वल टू b for 2 n is equal to 10 by n। तो आंसर आएगा कितना, ऑप्शन बी 10 by n। फिर आता है कि वेव ऑफ द फ्रीक्वेंसी 10 हर्ट्ज इज सेंट, wave of the frequency 4 hertz is sent along a string towards a fixed in. When this wave travels back after the reflection, a node is formed at a distance of 10 cm from the fixed end of the string. The speed of the incident and the reflected wave are, तो at the fixed end node, therefore the distance between two constructive node हो जाएगा लैम्डा बाई 2 इक्वल टू 10 सेंटीमीटर। लैम्डा जो है वेवलेंथ ऑफ द वेव फ्रंट है, लैम्डा हो जाएगा 20 सेंटीमीटर यानी कि 0.2 मीटर। एज वी नो v इक्वल टू हो जाएगा म्यू लैम्डा, तो v इक्वल टू हो जाएगा कितना 20 मीटर पर सेकंड। तो आंसर होगा ऑप्शन सी 20 मीटर पर सेकंड। अगला है कि स्टैंडिंग वेव इज रिप्रेजेंटेड बाय द इक्वेशन y इक्वल टू f 40 cos 0.01 x where x and y are in the millimeters, तो t in the second and x in the meter। तो वेलोसिटी ऑफ द वेव कितना हो जाएगा, तो द स्टैंडर्ड इक्वेशन ऑफ द स्टैंडिंग वेव इज y इक्वल टू f ओमेगा t प्लस cos kx, गिवन इक्वेशन इज y इक्वल टू f 40 और cos 0.01 x। कंपेयर करेंगे इक्वेशन 1 और 2 को, तो ओमेगा इक्वल टू हो जाएगा 4, k इक्वल टू आएगा 0.01। तो वेलोसिटी ऑफ द वेव आ जाएगा v इक्वल टू लैम्डा बाई टी यानी ओमेगा पे यानी 4 बाई 0.01 यानी कि 10 का पावर 4 मीटर पर सेकंड। तो आंसर इसका कितना जाएगा, आंसर का ऑप्शन इसका ए 10 का पावर 4 मीटर पर सेकंड। फिर आता है कि स्ट्रेचेज द स्ट्रिंग यूनिट विद ट्यूनिंग फॉर्क ऑफ द फ्रीक्वेंसी 512 हर्ट्ज, द लेंथ ऑफ द स्ट्रिंग इज 0.5 मीटर। द लेंथ ऑफ द स्ट्रिंग रिक्वायर्ड टू वाइब्रेट यूनिटली विद द ट्यूनिंग फॉर्क ऑफ फ्रीक्वेंसी 256 हर्ट्ज वुड बी, the frequency of the fundamental note of the stretched string is given by mu is equal to 1 by 12 root over t by mu, where t is the tension in the string, mu is the mass per unit length of the string। From the equation 1, mu जो होता है inversely proportional to 1 by L, तो as the string is same so mu will be same for the two different cases, mu1 by mu2 is equal to L2 by L1। तो mu1 is equal to 512 हर्ट्ज, L1 is equal to 0.5 मीटर, तो mu2 is equal to 256 हर्ट्ज, तो L2 कितना हो जाएगा, तो यहाँ से L2 निकालेंगे तो कितना आ रहा है 1 मीटर। तो आंसर आएगा ऑप्शन सी 1 मीटर। अगला है कि फॉर द प्रोडक्शन फॉर द बीट्स द टू फोर्सेज मस्ट बी, आंसर ऑप्शन बी कि डिफरेंट फ्रीक्वेंसी का होना चाहिए। When two sounds wave of the slightly different frequency travel in the medium along the same direction and superimpose on each other, the intensity of the resultant sound at a particular position rises and falls alternatively with the time. This phenomenon of the alternate variation in the intensity of the sound time at a particular position when the two sounds wave of the nearly equal frequency but not equal superimpose on each other is called the beats। फिर आता है कि a closed organ pipe closed at one index fighter to support the third overtone, it is found that air in the pipe has, so in a closed organ pipe only alternates harmonic for the frequency mu1, 3 mu1 and 5 mu1 etc. are present। The harmonics for the frequency 2 mu1, 4 mu1 and 6 mu1 are missing। In general, the frequency of the note produced in the nth normal mode of the vibration of the closed organ pipe would be bn is equal to 2n minus 1 b by 4l यानी 2n minus 1 mu1। अब यहाँ से करेंगे तो इस दे रही है 2n minus 1 हार्मोनिक और n minus 1 था ओवरटोन, तो थर्ड ओवरटोन है द फ्रीक्वेंसी 7 mu1 which means L is equal to 7 lambda by 4, तो L lambda by 2 plus lambda by 2 plus lambda by 2 plus lambda by 4 which is 3 full loops and a half loop which is equal to the 4 notes and 4 anti notes। तो आंसर है ऑप्शन डी 4 notes and 4 anti notes। अब डॉपलर इफेक्ट है जो नहीं आ रहा है, तो डॉपलर इफेक्ट का क्वेश्चन है जो नहीं आएंगे। अब वेव्स का देख लेते हैं एनसीईआरटी, हालांकि एनसीईआरटी का कुछ आया नहीं है लेकिन फिर भी क्विकली इसको देख लेते हैं, शायद स्टेटमेंट बेसिक क्वेश्चन बना के दे सकता है। तो इसका इंट्रोडक्शन में इन द प्रीवियस चैप्टर वी स्टडी द मोशंस ऑफ द ऑब्जेक्ट ऑसिलेटिंग इन isolation. What happens in a system which is collection of the such object? A material medium provides such an example. Here elastic forces bind or constrain to each other and therefore the motion of one affects that of the other. If you drop a little pebble in the pond of the still water, the pond surface gets disturbed. The disturbance does not remain confined to one place but propagates outward along the circle. If you continue dropping pebbles in the pond, you will see circles rapidly moving outward from the pond where the water source is disturbed. It gives a feeling as if the water is moving outward from the point of the disturbance. If you put some cork pieces on the disturbed surface, it is seen that the cork pieces move up and down but do not move away from the center of the disturbance. This shows that the water mass does not flow outward with the circles but rather a moving disturbance is created. Similarly, when we speak, the sound moves outward from us without any flow of the air from one part of the medium to another. The disturbances produced in the air are much less obvious and only our ears or microphone can detect them. This pattern which move without The actual physical transfer or the flow of the matter as a whole are called the waves. In this chapter, we will study such waves. The waves transport energy and the pattern of the disturbance such information that propagate from one point to another. All our communication is usually depend on the transmission of the signal through the wave. Of speech means productions of the sound waves in the air, and hearing amounts to their detection. Often communication involves different kinds of the waves. For example, sound waves may be the first converted to an electric current signal, which in turn may generate an electromagnetic wave that may be transmitted by an optical cable or via a satellite. Detection of the original signal will be usually involve these steps in the reverse order. Not all waves require a medium for their propagation. We know that light waves can travel through the vacuum. The light emitted by the stars, which are in hundreds of light years away, reaches us through interstellar space, which is practically vacuum. The most familiar type of the waves, such as the waves on a string, water waves, and the sound waves, seismic waves, etc., is so-called the mechanical waves. These waves require a medium for the propagation. They cannot propagate through a vacuum. They involve the oscillations of the constant particles and depend upon the elastic property of the medium. Electromagnetic waves that you will learn in the class 12 are different types of the waves. Electromagnetic waves do not necessarily require a medium. They can travel through the vacuum. Light, radio waves, X-ray, and all electromagnetic waves in vacuum. All electromagnetic waves have the same speed c, which value which इक्वल टू होता है इतना मीटर पर सेकंड. फिर आता है कि a third kind of wave is the so-called matter wave. They are associated with the constituents of the matter, electrons, protons, neutrons, atoms, and the molecule. They arise in the quantum mechanical descriptions of the nature that you will learn in your later studies. Though they are conceptually more abstract than the mechanical electromagnetic waves, they have already found applications in the several devices basic to the modern technology. Matter waves associated with electrons are employed in the electron microscope. In this chapter, we will study the mechanical waves which require a material medium for their propagation. The static influence of the waves on the art and the literature is seen from the early times, yet the first scientific analysis of the wave motion dates back to the 17th century. Some of the famous scientists associated with the physics of the wave motion are the Huygens, Hooke, Newton. The study of the physics of the wave followed by the physics of the oscillations of the mass tied to the spring and physics of the simple pendulum. Waves in the elastic media are intimately connected with the harmonic of the oscillation of stretched spring, coiled springs, etc. are examples of the elastic media. We shall illustrate this connection through the simple example. Consider a collection of the spring connected to one another as shown. If the spring at one is pulled friendly and released, the disturbance travels to the other end. What has happened? The first spring is disturbed from its equilibrium length. Since the second spring is connected to the first, it is also stretched or compressed and so on. The disturbance moves from the one end to the other, but each spring only executes and some oscillation about its equilibrium position. And a practical example of this situation concerns a stationary train at a railway station. Different bogies of the train are coupled to each other through a spring coupling. When an engine is attached at one end, it gives a push to the bogie next to it. This push is transmitted from the one bogie to another without the entire train being bodily displaced. Now let us consider the propagation of the sound wave in the air. As the wave passes through the air, it compresses or expands a small region of the air. This causes a change in the density of that region, say lambda p. This change induces a change in the pressure, lambda p in that region. Pressure is a force per unit area, so there is a restoring force proportional to the disturbance, just like in the spring. In this case, the quantity is similar to the extension or compression of the spring is the change in the density. If a region is compressed, the molecules in that region are packed together and they tend to move out of the adjoining region, thereby increasing the density or creating compression in the adjoining region. Consequently, the air in the first region undergo rarefaction. If a region is comparatively rarefied, the surrounding air will erosion, making the rarefaction more to the adjoining region. Thus, the compression or the rarefaction moves from the one region to another, making the propagation of the disturbance possible in the air. फिर आता है कि in solid similar argument can be made in the crystalline solid atoms or groups or atoms are arranged in a periodic lattice. In these, each atom or group of the atom is in the equilibrium due to the forces of the surrounding atoms. Displacing one atom, keeping the other fixed leads to the restoring forces, exactly in a spring. So we can think of the atoms in lattice as the endpoints with a spring between pairs of them. In the subsequent sections of this chapter, we are going to discuss various characteristic properties of the waves. फिर आता है transverse waves and longitudinal waves. So we have seen that motions for the mechanical waves involves the oscillations in the constituents of the medium. If the constituents of the medium oscillates perpendicular to the directions of the wave propagation, we call the wave a transverse wave. If they oscillate along the directions of the wave propagation, we call the longitudinal wave. Figure 4.1 for the propagation of the single pulse along a string, the resulting from a single up and down jerk. If the string is very long compared to the size of the impulse, the pulse will damp out before it reaches the other end and reflection from that end may be ignored. Figure 14.3 shows a similar situation, but this time the external agent gives a continuous periodic sinusoidal up and down jerk to the end of the string. The resulting disturbance on the string is then a sinusoidal wave. In other case, the elements of the string oscillate about their equilibrium mean position at the pulse or the wave passes through them. The oscillation are normal to the directions of the wave of motion along the string, so this is an example of the transverse wave. We can look at the wave into two ways. We can fix an instant of the time and picture of a wave in the space. This will give us to the shape of the wave as a whole in the space at a given instant. Another way is to fix a location that will fix our attention on a particular element of the string and see its oscillating motion in that time. फिर आता है Figure 14.4 describe the situations for the longitudinal wave in the most familiar example of the propagation of the sound wave. A long pipe filled with air has the piston at one end. A single sudden push forward and pull backward of the piston will generate a push of the condensation higher density and air fraction lower density in the medium air. If the pull of the piston is continuous and a periodic sinusoidal, a sinusoidal wave will be generated propagating in the air along the length of the pipe. This is clearly an example of the longitudinal wave. The wave considered above transverse for the longitudinal are traveling or progressive wave since they travel from the one part of the medium to another. The material medium as a whole does not move as already noted. A stream, for example, constitutes motion of the water as a whole. In a water wave, if the disturbance that moves not water as a whole, likewise, a wind motion of the air as a whole should not be confused with a sound wave, which is propagation of the disturbance in the peripheral density in the air without the motions of the air medium as a whole. In transverse wave, the particle's motion is normal to the directions of the propagation of the wave. Therefore, as the wave propagates, each element of the medium undergoes a shearing of strain. Transverse waves can therefore be propagated only in those media which can sustain the shearing of strain, such as the solids and in the fluids. Fluids as well as the solids can sustain the compressive strain. Therefore, the longitudinal waves can be propagated in elastic media. For example, in a medium like the steel, both transverse and the longitudinal waves can be propagated, while air can sustain only the longitudinal wave. The waves on the surface of the water are two kinds: capillary waves and the gravity waves. The former of the ripples of the fairly short wavelength, not more than a few centimeters, and the restoring force that produces them in the surface tension of the water. Gravity waves are the wavelength typically ranging from the several meters to the several hundreds meters. The restoring force that produces these waves is the pull of the gravity, which tends to keep the water surface at its lowest level. The oscillations of the particle in these waves are not confined to the surface only, but extend with the diminishing amplitude of the at very bottom. The particle motion in the water waves involves a complicated motion. They not only move up and down but also back and forth. The waves in an ocean are the combinations of the both longitudinal and a transverse wave. It is found that generally transverse wave and longitudinal waves travel with a different speed in the same medium. अब यहाँ पर दिया given below are some examples of the wave motion. State in each case if the wave motion is transverse, longitudinal, or a combination of both. The motion of a kink in the longitudinal spring produced by the displacing one end of the spring sideways, तो ये हो जाएगा transverse and longitudinal. Wave produced in a cylinder containing a liquid by moving its piston back and forth, तो ये हो जाएगा longitudinal. फिर wave is produced by the motorboat sailing in the water, तो ये हो जाएगा transverse and longitudinal. फिर आता है कि ultrasonic waves in the air produced by a vibrating quartz crystal, तो ये हो जाएगा longitudinal. अब आता है displacement relation in a progressive wave. So for mathematical description of a traveling wave, we need a function of both position x and the time t. Such a function at every instant should give the shape of the water wave at that instant. Also at every given location, it should describe the motion of the constituents of the medium at that location. If we wish to describe a sinusoidal traveling wave such as the one shown in the figure 14.3, the corresponding function must also be sinusoidal. For convenience, we also take the wave to transfer so that if the positions of the constituent of the medium is denoted as x, the displacement from the equilibrium position may be denoted by y. A sinusoidal traveling wave is therefore described by y x comma t equal to f and kx minus omega t plus phi. The term phi in the argument of the sine function means equivalently that we are considering a linear combination of the sine and the cosine function. Y x comma t equal to f and kx minus omega t plus p cos kx minus omega t. From the equation 14.2 and 14.3, a is equal to root over a square plus b square or phi equal to tan inverse p by a. फिर आता है कि to understand y equation 14.2 represents a sinusoidal traveling wave. Take a fixed instant, set t is equal to t naught. Then the argument of the sine function in the equation 14.2 is simply kx per hour constant. Thus the shape of the wave at any fixed instant as a function of the x is a sine wave. Similarly, take a fixed location phi equal to x naught. Then the argument of the sine function in the equation is constant minus omega t. The displacement by at a fixed location thus varies sinusoidally with the time. That is the constituent of the simple of the medium at a different position execute a simple harmonic motion. Finally, as the xt increases, x must increase in the positive direction to keep the k minus omega t plus phi constant. Thus, the equation 14.2 represents a sinusoidal harmonic wave traveling along the positive direction along the x-axis. On the other hand, y x comma t a fan kx plus omega t plus phi represents a wave traveling in the negative direction of the x-axis. Figure 14.5 gives the names of the various physical quantity appearing in the equation 14.2 that we now represent. तो y x comma t जो हो गया वो डिस्प्लेसमेंट एज ए फंक्शन फॉर द पोजीशन x and the time t, a जो हो गया एम्पलीट्यूड ऑफ द वेव, ओमेगा जो हो गया एंगुलर फ्रीक्वेंसी ऑफ द वेव, k हो गया एंगुलर वेव नंबर और kx माइनस ओमेगा t प्लस 5 हो गया इनिशियल फेज a प्लस x is 0 t equal to 0. Figure 14.6 for the plots for a different value of the time varying by the equal interval of the time. In a wave, the drift is the point of the maximum positive displacement, the trough is the point of the maximum negative displacement. To see how a wave travels, we can fix attention on the drift and see how it can progress with the time. In the figure, this is shown by the cross on the drift. In the same manner, we can see the motions of a particular constants of the medium at a fixed location. Say at the origin of the x-axis. This is shown by a solid dot. The plot of this figure 14.6 shows that with time the solid dot at the origin moves periodically. That means the particle at the origin oscillates about its mean position as the wave progresses. This is true for any other location also. We also see that during that time the dot has completed one full cycle. The drift has moved up by a certain distance. यहाँ पर दिखाया हुआ harmonic wave progressing along the positive directions of the x-axis at a different times. Using the plot figure 14.6, we now define the various quantity of the equation 14.2. फिर आता है amplitude and the phase. In the equation 14.2, since the fun function vary between the 1 and minus 1, the displacement by x comma t vary between the a and minus 1 a. We can take a to be positive constant but without any loss of the generality. The a represents the maximum displacement of the constant of the medium from their equilibrium position. Note that the displacement by may be positive or negative, but if a is positive, it is called as the amplitude of the wave. The quantity kx minus omega t plus phi appearing as the argument of the fun function is called the phase of the wave. Given the amplitude a, the phase determines the displacement of the wave at any position and at any instant. Clearly, phi is the phase at x बराबर 0 and t बराबर 0. Hence, phi is called the initial phase and angle. By suitable choice of the origin on the x-axis and the initial time, it is possible to have phi equal to 0. Thus, there is no loss of the generality in dropping phi. That means when taking equation 14.2 with phi equal to 0. फिर आता है wavelength and the angular wave number. So the minimum distance between 2 points having the same phase is called the wavelength of the wave, usually denoted by lambda. For simplicity, we can choose the points of the same phase to be drift or the trough. The wavelength is then the distance between the two consecutive drift or the trough in the wave. Taking phi equal to 0 in the equation 14.2, the displacement t equal to 0 is given by x comma equal to f and kx. Since the fan function repeats with value after the every 2 pi change, the fan kx is equal to fan 2 kx plus 2 n pi and fan k x plus 2 n pi by k, that is the displacement at the points x and x equal to 2 n plus 2 n pi by k are the same where n equal to 1 to 3. The lift distance between the points with the same displacement at any given instant of the time is obtained by taking n equal to 1. Lambda is then given by lambda equal to 2 pi by k or k equal to 2 pi by lambda. K is the angular wave number of the propagation constant. Its unit is radian per meter or the radian per meter. फिर आता है period, angular frequency and the frequency. So figure 14.14 again the sinusoidal plot. It describes not the shape of the wave at a certain instant but the displacement of the element at any fixed location of the medium as a function of the time. B may for simplicity take equation 14.2 with phi equal to 0 and monitor the motion of the element f(x) for 0. B then get y0 comma t equal to f1 minus omega t यानी कि माइनस f1 omega t. अब इसके बाद फिर आता है कि now the period of the oscillation of the wave is the time it takes for the element to complete one oscillation, that is minus f1 omega t equal to minus f1 omega t plus capital T minus f1. Since fan function repeats after every 2 pi, omega t equal to 2 pi or omega to 2 pi by t. Omega is called the angular frequency of the wave. Its unity radian per second. The frequency mu is the number of the oscillation per second. Therefore, mu is equal to 1 by t equal to omega by 2 pi. Where mu is measured in the hertz. In the discussion above, reference has always been made to the wave traveling along a string or a transverse wave. In the longitudinal wave, the displacement of an element of the medium is parallel to the directions of the propagations of the wave. That the displacement function for the longitudinal wave is written as x comma t equal to f and k minus omega t plus phi, where x comma t the displacement of an element of the medium in the directions of the propagations of the wave at a position x and a time t. A the displacement amplitude other quantity have the same meaning as in the case of a transverse wave except that the displacement function by x comma t to be replaced by the function f x comma t. फिर यहाँ पर दिया हुआ है कि a wave traveling along a string is described by y x comma t equal to 0.05 फाइन 80x minus 3.0t, in which the numerical constant are in the SI unit, यानी 0.05 meter, 0.80 radian per meter, and the 3 radian per second. Calculate the amplitude of the wavelength and the time period and the frequency of the wave. Also calculate the displacement of the body of the wave at a distance x equal to 30 centimeter and t equal to 20 second. So on comparing this displacement equation with the y is equal to x comma t, a equal to sin k x minus omega t, we find the amplitude of the wave is 0.005 meter and 5 mm. The angular wave number k and the angular frequency omega are k is equal to 80 meter per meter inverse and omega is equal to 3 second inverse. We then relate the wavelength lambda to the k through the equation lambda equal to 2 pi by k and 2 pi by 80 per meter and 1.85 centimeter. Now we relate t to the omega by the relation t is equal to 2 pi by omega to 2 pi by 3 and 2.09, and frequency mu equal to 1 by t. The displacement by at x equal to 30 centimeter and at t equal to 20 second is given by इतना. तो the speed of a traveling wave. अब इसके बाद आता है कि to determine the speed of a propagation of a traveling wave, we can fix our attention on any particular point on the wave characterized by the some value of the phase and see how that point moves at a time. It is convenient to look at the motions of the crest of the wave. Figure 14.8 gives the shape of the wave at the two instants of the time, which differ by a small time interval delta t. The entire wave pattern is seen to shift to the right positive direction of the x-axis by a distance delta x. In particular, the crest function by dot moves distance delta x in the time delta t. The speed of the wave is then delta x by delta t. We can put a dot on a point with any other phase. It will move with the same speed v. Otherwise, the wave pattern will not remain fixed. The motions of the motion fixed point on the wave is given by x minus omega t equal to constant. फिर आता है कि thus as the time t changes, the position x of the fixed phase point must change so that the phase remains constant. Thus, the kx minus omega t equal to kx plus delta x, यानी minus omega t plus delta t, or k delta x is equal to minus omega delta t is equal to 0. Taking delta x for delta t minus small, this gives dx by dt is equal to omega by k is equal to v. And letting omega to t and k to the lambda, we have v is equal to 2 pi by v by 2 pi by lambda, यानी lambda v is equal to lambda by t. Equation 14.12, a general relation for all the progressive waves, so that in the time required for one pole oscillation y and the constant of the medium, the wave pattern travels a distance equal to the wavelength of the wave. It should be noted that the speed of the mechanical wave is determined by the inertial yani linear mass density for the string, mass density in general, and elastic property Young modulus of the linear media, shear modulus, bulk modulus of the medium. The medium determines the speed, then relates the wavelength to the frequency of the given speed. Of course, as remarked earlier, the medium can support both transverse and longitudinal waves, which will have different speed in the same medium. Later in this chapter, we shall obtain the specific expression for the speed of the mechanical waves in the same medium. The speed of a transverse wave on a stretched string. So the speed of a mechanical wave is determined by the restoring force set up in the medium, which is disturbed, and the inertial property, mass and density of the medium. The speed is expected to be directly related to the former and inversely related to the latter. For waves on a string, the restoring force is provided by the tension T in the string. The inertial property, which in the case be linear, mass density mu, which is the mass of the string divided by the length. Using the Newton's law of the motion, and the exact formula for the wave speed on the string can be derived. But this derivation is outside the scope of this book. We shall therefore use a dimensional analysis. We already know that dimensional analysis alone can never yield the exact formula. The overall dimensionless constant is always left undetermined by the dimensional analysis. तो यहाँ पर फिर आता है कि डायमेंशन ऑफ द म्यू इज ml minus 1 and that of the t is like force ml t minus 2, and we need to combine these dimensions to get the dimensions of the speed v ult minus 1. Simple inspection so that the quantity t by mu has the relevant dimension and L2 t minus 2. Thus, if the t and mu are assumed to be the only relevant physical quantity, so v is equal to c root over t by mu, where c is the undetermined constant of the dimensional analysis. In the exact formula, it transfers that c is equal to 1. The speed of the transverse wave on a stretching is given by v is equal to root over t by mu. Note an important point that the speed v depends only on the property of the medium t, and mu t is a property of the stretched string arising due to an external force. It does not depend on the wavelength or the frequency of the wave itself. In higher study, you will come across the waves whose speed is not independent of the frequency of the wave. Of the two parameters, lambda and mu is the source of the disturbance, determine the frequency of the wave generated. Given the speed of the wave in the medium and the frequency, equation 14.12 then fix the wavelength lambda is equal to mu by v. A steel wire of the 0.12 meter long has a mass of the 5.0 गुना 10 to the power -3 kg if the bar is under a tension of the 50 Newton. What is the speed of the transverse wave on the wire? तो mass per unit length of the wire होता है mu equal to 5 गुना 10 to the power -3 kg by 0.72 and 6.9 गुना 10 to the power -3 kg meter inverse. Tension T equal to 50 Newton. The speed of the wave on the string given by v equal to root over T by mu. तो कितना आ जाएगा 93 मीटर पर सेकंड। फिर आता है speed of the longitudinal wave, speed of the sound. So in the longitudinal wave, the coefficients of the medium oscillate forward and backward in the directions of the progression of the wave. We have already seen that sound waves travel in the form of the compression and rarefaction of the small volume element of the air. Elastic property that determines the stress under the compressional strain is the bulk modulus of the medium defined by the beta equal to minus delta P by delta V by B. Here the change in the pressure delta P produces a volumetric strain delta V by B. B has the same dimension as the pressure and given in the SI units in terms of the Pascal. The inertial property relevant for the propagation of the wave is the mass density rho with dimension ml minus 3. Simple inspection reveals that the quantity B by rho has the relevant dimension L2 T minus 2. If the beta and rho are considered to be the only relevant physical quantity, so V is equal to C root over B by rho, where as before C the underdetermined constant for the dimensional analysis. The exact derivation for that C is equal to 1. Thus the general formula for the longitudinal wave in the medium is mu is equal to root over B by rho. For a linear medium like solid bar, the lateral expression for the bar is negligible and we may consider it to be only under longitudinal strain. In that case, the relevant modulus of the elasticity is the Young modulus, which has to be same dimension as the bulk modulus. Dimensional analysis for this case is the same as before and also a relation like equation 14.18 with a underdefined C. With the exact derivation for to be unity. Thus, the speed of the longitudinal wave in a solid bar given by gamma is V equal to root over gamma by rho, where Y is the Young modulus of the material of the bar. Equation table 14.1 gives the speed of the sound in the some media. इसके बाद फिर आता है कि liquids and the solids generally have the higher speed of the sound than the gases. Not for the fault the speed being referred to as the speed of the longitudinal wave in the solid. This happens because they are much more difficult to compress than the gases and have so much higher value of the bulk modulus. Now see equation 14.19. Solids and liquids have higher mass density rho than the gases, but the corresponding increase in both the modulus of the solids and liquid is much higher. This is the reason why the sound waves travel faster in the solid than the liquid. We can estimate the speed of the sound in a gas in the ideal gas approximation. But in ideal gas, the pressure P, volume V, and temperature T are related by the P is equal to N kBT, where N is the number of the molecules in the volume, Kb the Boltzmann constant, T is the temperature of the gas in the Kelvin. Therefore, for the isothermal change, it follows that V delta P plus P delta V is equal to 0, and delta P by minus delta P by delta V by B is equal to P. And substituting the equation 14.16, we have B is equal to P. Therefore, from the equation 14.19, the speed of the longitudinal wave in ideal gas is V is equal to root over P by rho. This relation by first given by the Newton and known as the Newton's formula. Estimate the speed of the sound in the air at a standard temperature and the pressure. The mass of the 1 mole of the air is 29 to the power minus 3 kg. So we know that 1 mole of any gas occupies 22.4 liter at FTP. Therefore, density of air at FTP is rho naught is equal to mass of the 1 mole of the air by volume of the 1 mole of the FTP. 29 गुना 10 power minus 10 by 22.4 गुना 10 power minus 3 मीटर पर मीटर क्यूब यानी 1.29 kg पर मीटर क्यूब आ जाएगा. अब इसका आगे बोलता है कि अकॉर्डिंग टू न्यूटन फार्मूला फॉर द स्पीड ऑफ द साउंड इन द मीडियम वी गेट द स्पीड फॉर द साउंड इन द एयर एट FTP v इज इक्वल टू 1.05 बाय 1.29 के 1/2 यानी आएगा 280 मीटर पर सेकंड. द रिजल्ट फाउंड इन इक्वेशन 14.23 इज अबाउट 15% ऑफ स्मॉल एज कंपेयर्ड टू द एक्सपेरिमेंटल वैल्यू ऑफ द 331 मीटर पर सेकंड आई गिवन एट टेबल 14.1 वेयर. So if we examine the basic assumption made by Newton that the pressure variation in the medium during the propagation of the sound are isothermal, we find that this is not correct. If it is pointed out by Laplace that the pressure variation in the propagation of the sound waves are so fast that there is little time for the heat flow to maintain constant temperature. These variations therefore are adiabatic and not isothermal. For adiabatic process, the ideal gas satisfies the relation PV gamma is equal to constant. So delta PV gamma is equal to 0. So P gamma V gamma minus 1 into delta V plus V gamma delta P is equal to कितना था 0. Where gamma is the ratio of the two specific heat Cp by Cv. Thus, for ideal gas, the adiabatic bulk modulus given by B adiabatic is equal to minus delta P by delta V by B. So, the speed of the sound is therefore 14.19 given by V is equal to root over gamma P by rho. This modification of the Newton's formula is referred to as the Laplace correction. For here, gamma is equal to 1 by 5. Now using equation 14.24 to estimate the speed of the sound in the air at FTP, we get a value of 3.3 meter per second, which agree with the measured speed. फिर आता है the principle of the superpositions of the wave. तो what happens when two waves pulse traveling in the opposite direction traveling in the opposite direction cross each other. It turns out that the wave pulses continue to retain their identity after they have crossed. However, during the time they overlap, the wave pattern is different from either of the pulses. Figure 14.9 for that situation when the two pulses are equal and opposite shape move towards each other. When the pulses overlap, the resultant displacement of the algebraic sum of the displacement due to each pulse. This is known as the principle of the superposition of the wave. According to this principle, each pulse moves as if the others are not present. The constituents of the medium therefore suffer displacement due to the both, and since the displacement can be positive and negative, the net displacement is an algebraic sum of the two. Gives Figure 14.9 gives the graph of the wave shape at the different times. Note the dramatic effect in the graph. The displacement due to the two pulses have exactly cancelled each other, and there is zero displacement throughout. To put the principle of the superposition mathematically, let y1 x comma t and the y2 x comma t to be the displacement due to the two waves disturbances in the medium. If the wave arrives in a region simultaneously and therefore overlap, the net displacement by x comma t given by y x comma t equal to y1 x comma t plus y2 x comma t. यहाँ पर आता है the two pulses having the equal and the opposite displacement moving in the opposite direction. The overlapping pulse add up to the zero displacement in the curve C. फिर आता है कि if we have two or more waves moving in the medium, the resultant wave form is the sum of the wave functions of the individual wave. That is, if the wave function of the moving waves are y1 is equal to f1 x minus bt or y2 is equal to f2 x minus bt, so yn is equal to fn x minus bt. Then the wave function describing the disturbance in the medium is y equal to f1 x minus bt plus f2 x minus bt plus fn x minus bt हो जाता है. The principle of the superposition is the basic to the phenomena of the interference. For simplicity, consider two harmonic traveling waves on a stage string, both with the same omega angular frequency and the k wave number, and therefore the same wavelength lambda. Their wave speed will be identical. Let us further assume that the amplitude are equal and they are both traveling in the positive direction of the x-axis. The waves only differ in their initial phase. According to the equation 314.2, the two waves are described by the function by 1 x comma t equal to f1 kx minus omega t or by 2 x comma t equal to f1 kx minus omega t plus phi. The net displacement is then by the principle of the superposition y x comma t equal to f1 kx minus omega t plus f1 kx minus omega t plus phi. So where we have used the familiar trigonometric identity sin a plus b, we then have y x comma t equal to a cos phi by 2 is equal to sin x minus omega t plus phi by 2. Equation 14.31 is a harmonic traveling wave in the positive direction of x-axis with the same frequency and the wavelength. However, its initial phase angle is phi by 2. The significant thing is that its amplitude is a function of the phase difference phi between the constituent two waves. A phi equal to 2a cos half phi. For the phi equal to 0, we have the when the waves are in phase y x comma t equal to a sin kx minus omega t. That means the resultant wave has the amplitude 2a. The largest possible value of the a for the phi equal to pi. The waves are completely out of phase and the resultant waves have the zero displacement everywhere at all the times. So y x comma t equal to 0. Equation 14.33 refers to the so-called constructive interference of the two waves where the amplitude add up in the resultant wave. 14.34 is the case of the destructive interference where the amplitude subtract out in the resultant wave. Figure 14.10 for these two cases of the interference of the wave rising from the principle of the superposition. फिर आता है reflection of the wave. So far we considered wave propagating in an unbounded medium. What happens if a pulse or a wave meets a boundary? If the boundary is rigid, the pulse or the wave gets reflected. The phenomena of the echo is an example of the reflection by a rigid boundary. If the boundary is not completely rigid or in the interface between the two different elastic media, the situation is somewhat complicated. A part of the incident wave is reflected and a part is transmitted into the second medium. If a wave is incident obliquely on the boundary between the two different media, the transmitted wave is called a refracted wave. The incident and the refracted wave obey the Snell's law of the refraction, and the incident and the reflected wave obey the usual law of the reflection. Figure 4.11 for a wave pulse traveling along a stretched string and being reflected by the boundary. Assuming there is no absorption of the energy by the boundary, the reflected wave has the same shape as the incident pulse, but it suffers a phase angle of the pi or 180 degree on the reflection. This is because the boundary is rigid and the disturbance must have the zero displacement at all the time of the boundary. By the principle of the superposition, this is possible only if the reflected and the incident wave differ by a phase angle of pi, so that the resultant displacement is zero. This reading is based on the boundary condition on a rigid ball. We can arrive at the same conclusion dynamically also, as the pulse arrives at the wall, it exerts a force on the ball. By the Newton's third law, the ball exerts an equal and opposite force on the string, generating a reflected pulse that differs by a phase of the pi. तो यहाँ पर देखो रिफ्लेक्शन ऑफ ए पल्स मीटिंग एट ए रिजिड बाउंड्री पर ये दिखाया हुआ है. फिर आता है कि ऑन द वन अदर हैंड द बाउंड्री पॉइंट इज नॉट रिजिड बट कम्प्लीटली फ्री टू मूव सच एज इन द केस ऑफ द स्ट्रिंग टाइड टू द फ्री मूविंग free moving ring on a road. The reflected pulse has the same phase and amplitude, assuming no energy dissipation as the incident pulse. The net maximum displacement at the boundary is then twice the amplitude of each pulse. An example of the non-rigid boundary is the open and the end of an organ pipe. To summarize, a traveling beam or a pulse suffers a phase angle of the pi on a reflection at a rigid boundary and no phase change on the reflection at an open boundary. To put this mathematically, let the incident traveling wave be pi 2x, t equal to f1 k x minus omega t. At a rigid boundary, the reflected wave is given by pi 1 x, t equal to f1 k x minus omega t plus minus plus pi or minus f1 k x minus omega t. At an open boundary, the reflected wave is given by x, t equal to f1 k x minus omega t plus 0 or f1 k x minus omega t. Clearly, the rigid boundary pi is equal to pi 1 2 plus pi are equal to 0 at all times. Path of standing waves and the normal waves and the normal modes to be considered above reflection at one boundary, but there are family of situations if stream fixed at either end or an air column in a pipe with either end closed, and with the reflection take place at two or more boundaries. In a stream, for example, a wave traveling in the one direction will get reflected at one end, which in turn will travel and get reflected from the other end. This will go until there is a steady wave pattern set on the string. Such wave patterns are called the standing wave or the stationary wave. To see this mathematically, consider a wave traveling along the positive direction of the x-axis and a reflected wave of the same amplitude and wavelength in the negative direction of the x-axis. From the equation 14.2 and 14.4 with phi equal to 0, we get y1 x, t is equal to f1 k x minus omega t, y2 x, t equal to f1 k x plus omega t. The resultant beam on the string is accordingly to the principle of the superposition. The y x, t equal to y1 x, t plus y2 x, t. जहाँ ए फाइन के एक्स माइनस ओमेगा टी प्लस फाइन के एक्स प्लस ओमेगा टी हो जाएगा यूजिंग द फैमिली ट्रिग्नोमेट्रिक आइडेंटिटी फाइन ए प्लस बी इक्वल टू फाइन प्लस फाइन ए माइनस बी इक्वल टू 2 फाइन ए कॉस बी गेट वाई एक्स कॉमा टी इक्वल टू ए फाइन के एक्स कॉस ओमेगा टी नोट दैट इंपॉर्टेंट डिफरेंस इन द बी पैटर्न डिस्क्राइब्ड बाय इक्वेशन 14.37 from that described by the equation 14.2 or the equation 14.4. The terms x and omega t appear separately, not in the combination x minus omega t. The amplitude of this wave is 2f and x. Thus, in the wave pattern, the amplitude varies from the point to point, but each element of the string oscillates with the same angular frequency omega on the time period. There is no phase difference between the oscillations of the different elements of the wave. The string as a whole vibrates in phase with the different amplitude at the different points. The wave pattern is neither moving to the right nor to the left. Hence, they are called the standing or the stationary wave. The amplitude is fixed at a given location, but as I remarked earlier, it is different at different locations. The point at which the amplitude is 0, where there is no motion at all. Notes: the point at which the amplitude is largest are called antinodes. Figure 4.14.1 to show the stationary wave pattern resulting from the superposition of the two traveling waves in opposite direction. The most significant feature of the stationary wave is at the boundary condition constant on the partial wavelength of the frequency of the vibration of the ecosystem. The system cannot oscillate with any arbitrary frequency, contrast with this with the harmonic traveling wave, but is characterized by the effect of the natural frequency or the normal modes of the oscillation. Let us determine these normal modes of the stitch shifting fixed at potent. First, from the equation 14.37, the positions of the nodes where the amplitude is 0 are given by sin kx equal to 0, which implies kx equal to n pi and n by 0, 1, 2, 3. Since k is equal to 2 pi by lambda, we get x equal to n lambda by 2 यानी n is equal to 0, 1, 2, 3. फिर यहाँ पर दिया हुआ है कि stationary waves have arising from the superposition of the two harmonic waves traveling in the opposite direction. Note that the position of the zero displacement remain fixed at all times. फिर आता है कि clearly the distance between any two successive nodes is lambda by 2. In the same way, the position of the antinodes where the amplitude is the largest are given by the largest value of the sin kx. The mod of sin kx is equal to 1, which implies kx is equal to n plus 1 by 2 pi, n is equal to 0, 1, 2, 3. With k is equal to 2 pi by lambda, we get x is equal to n plus half lambda by 2, n is equal to 0, 1, 2, 3. Again, the distance between any two consecutive antinodes is lambda by 2. Figure 14.38 can be applied to the case of the stitch string of the length L fixed at both ends, taking the one boundary to be at x power 0. The boundary condition at x power 0 and x power L are position of the nodes. Then x power 0 condition is already satisfied. The x power L node condition requires that the length L is related to the lambda by the L is equal to n lambda by 2, where n is equal to 1, 2, 3. Thus, the possible wavelength of the stationary wave are constrained by the relation lambda is equal to 2L by n, where n is equal to 1, 2, 3 with corresponding frequencies. So V is equal to nv by 12 for n is equal to 1, 2, 3. We have thus obtained the natural frequency, the normal modes of the oscillation of the system. The lowest possible natural frequency of the system is called the fundamental mode or the first harmonic. For the stretch of the string fixed at either end, it is given that V is equal to V by mu is equal to V by 12 corresponding to n by 1. Here mu is the speed of the wave determined by the property of the medium. The n by 2 frequency is called the second harmonic, n by 3 the third harmonic, and so on. We can label the value of harmonics by the symbol Bn equal to n equal to 1, 2, 3. Figure 14.134 that the first fixed harmonic of a stretching string fixed at either end. A string need not vibrate in one of these modes only. Generally, the vibration of the string will be superposition of the different modes. Some modes may be more strongly excited and some less. Musical instruments like the sitar or violin are based on this principle. When the string is plucked or bowed, determines which modes are more prominent than the others. Let us consider next normal modes of the oscillation for an air column with one included. तो यहाँ पर दिया हुआ द फर्स्ट सिक्स हार्मोनिक्स ऑफ द वाइब्रेशन ऑफ स्ट्रेचिंग स्ट्रिंग फिक्स्ड एट बोथ एंड पर दिया हुआ तो ये हो गया फंडामेंटल फर्स्ट हार्मोनिक सेकंड हार्मोनिक थर्ड हार्मोनिक फोर्थ हार्मोनिक फिफ्थ हार्मोनिक यहाँ पर दिया हुआ है सिक्स्थ हार्मोनिक। फिर इसके बाद आता है कि एंड अदर ऑर्गन and the other open. A glass tube partially filled with the butter illustrates the system. The end in the contact with the butter is a node, while the open end is an antinode. At the node, the preferred changes are the largest, while the displacement is the minimum. At the open end, the antinode is just the other way. Least preferred changes are maximum amplitude of the displacement. Taking the end in the contact with the butter to be x by 0, the node condition is already satisfied. If the other end x by L is an antinode, then the L is equal to n plus 1 by 2 L, lambda by 2 is equal to n is equal to 0, 1, 2, 3. The possible wavelength of them are then restricted by the definition lambda is equal to 2L by n plus half for n is equal to 0, 1, 2, 3. The normal modes, the natural frequency of the system are mu is equal to v n plus 1 by 2 v by 2L. The fundamental frequency corresponds to the n by 0 and is given by v by 4L. The higher frequency of the odd harmonics, that means the odd multiples of the fundamental frequency 3 by 4L, 5 by 4L, etc. Figure 14.1 for the first 6 odd harmonics of the air column with one end closed and the other end open. For a pipe open at both ends, each end is an antinode. It is then easily seen that an open air column at both ends generate all the harmonics. The system of strings and air columns can also undergo pulsed oscillation. If the external frequency is close to the one of the natural frequency, the system for the resonance. Normal modes of a circular membrane are readily clamped to the circumference as in the tabla are determined by the boundary condition that no points on the circumference of the membrane vibrates. Estimations of the frequency of the normal modes of the system is more complex. This problem involves the wave propagation in the two dimensions. However, the underlying physics is the same. If a pipe 30 cm long is open at both ends, which harmonic mode of the pipe resonate at 1.1 kHz force? Will the resonance speed the same force be observed if one end of the pipe is closed? Take the speed of the sound in the air 1840 meter per second. The first harmonic frequency given by V1 is equal to V by lambda 1 and V by 12, where L is the length of the pipe. The frequency in the nth harmonic is Vn is equal to NV by 12, जहाँ n जो कितना है 1, 2, 3 है ओपन पाइप. First few modes for open pipe are shown by the figure 14.15 for L by about 30 cm, V by about 350 meter per second. Vn is equal to n into 350 meter per second by 0.6 and 550 n per second. Clearly, a force of the frequency of the 1.1 kHz will be resonate at V2, that means the second harmonic. फिर आता है यहाँ पर दिया हुआ सेवंथ हार्मोनिक, फिर दिया हुआ है यहाँ पर नाइन्थ हार्मोनिक, फिर दिया हुआ है यहाँ पर 11th हार्मोनिक. The normal mode of an air column open at one end and closed at the other end. Only the odd harmonics are seen to be the possible. Now, if one end of the pipe is closed, it follows from the equation 14.15 that the fundamental frequency is V1 is equal to V by lambda 1 and V by 4L. Pipe closed at one end, and only the odd harmonics are present. So V3 is equal to 3V by 4L, V5 is equal to 5V by 4L. For L बराबर 30 cm, V बराबर 330 meter per second. The fundamental frequency of the pipe closed at one end is 75 Hz, and the fourth frequency correspond to this fourth harmonic. Since this harmonic is not partial mode, no resonance will be observed with the force the moment of the one end is closed. अगला टॉपिक है बीट्स. तो बीट्स ये इंटरेस्टिंग फिनोमेना arising from the interference of the wave when two harmonic sound waves of the closed but not equal frequency are heard at the same time. We hear the sound of the similar frequency, the average of the two closed frequency, but we hear something else also. We hear audibly distinct waxing and waning of the intensity of the sound, with the frequency equal to the difference in the two closed frequency. Artists with this phenomena by tuning their instrument with each other, they go on tuning until the sensitivity where do not detect any beats. To see this mathematically, let's consider two harmonic sound of the nearly equal angular frequency omega 1 and omega 2 and fix the location x to be 0 for the convenience. Figure 14.2 with a suitable choice for the past 5 equal to pi by 2 for each, and assuming the equal amplitudes give f1 is equal to a cos omega t, f2 equal to a cos omega 2t. Here we have replaced the symbol y by f since we are referring to the longitudinal note on the transverse displacement. Let omega 1 be the slightly greater of the two frequencies. The resultant displacement is by the principle of the superposition f equal to f1 plus f2 and a cos omega 1t plus a cos omega 2t. Using the familiar trigonometry identity for the cos A plus cos B, 2A cos omega 1 minus omega 2 by 2t, cos omega 1 plus omega 2 by omega t by 2, which may be written as f is equal to 2a cos omega vt cos omega at। तो ओमेगा 1 माइनस ओमेगा 2 का मॉड होगा लेस देन ओमेगा 1 होगा, और ओमेगा 2 और ओमेगा ए मच ग्रेटर देन ओमेगा बी। तो ओमेगा बी इक्वल टू ओमेगा 1 माइनस ओमेगा 2 by t and omega a equal to omega 1 plus omega 2 by 2. Now if we assume mod of omega 1 minus omega 2 is less than much less than omega 1, which means that omega a much greater than omega b, we can interpret the given 14.41 as follow. The resultant may be oscillating with the average angular frequency omega a, however its amplitude is not constant in the time. Unlike a pure harmonic wave, the amplitude is the largest when the term cos omega vt takes its limit plus or minus 1. In other words, the intensity of the resultant wave backphase and bends with the frequency, which is 2 omega b equal to omega 1 minus omega 2. Since omega is equal to pi v, the bit frequency b bit is given by b bit equal to mu1 minus mu t. Figure 14.1 figure illustrates the phenomena of the bits of the two harmonic waves for the frequency 11 Hz and 9 Hz. The amplitude of the resultant wave for the bits for the frequency 2 Hz. यहाँ पर there are four propositions of the two harmonic waves, one of the frequency 11 Hz and the other of the frequency 9 Hz, give rising to the bit for the frequency 2 Hz as shown in the figure C. फिर यहाँ पर आता है दिए हुए स्टैंडिंग वेव्स इन द ओपन पाइप फर्स्ट फोर हार्मोनिक आर डिपिक्टेड। यहाँ पर दिया फंडामेंटल और फर्स्ट हार्मोनिक, सेकंड हार्मोनिक, थर्ड हार्मोनिक और ये हो गया अपना फोर्थ हार्मोनिक। ये दिया हुआ है फंडामेंटल और फर्स्ट हार्मोनिक, थर्ड हार्मोनिक और फिफ्थ हार्मोनिक, क्योंकि जब वन इंक्लूड होता है तो सिर्फ ऑड हार्मोनिक होता है, जब टू इंक्लूड होता है तो ऑड और इवन दोनों ही हो जाते हैं। अब क्वेश्चन है कि फिगर 2 सितार string A and B playing the note are slightly out of the tune and bits produce match Hz. The tension of the string B is slightly increased and the bit frequency found to be decreased to 3 Hz. So what is the original frequency of the B if the frequency of A is 445 Hz? To increase in the tension of the string, increase its frequency. If the original frequency of the B BB were greater than that of the A BA, further increase in the BB should be have resulted in an increase in that of the bit frequency, but the bit frequency is found to decrease. This show that BA is less than BB, since BA minus BB is 5 Hz, तो BA इक्वल टू 427 Hz, BB इक्वल टू 422 Hz। फिर उसके बाद आता है इसका समरी में कुछ दिए हुए। तो समरी में क्या है कि mechanical waves can be used in material media and governed by the Newton's law. Mechanical waves can be used in the material media and are governed by the Newton's law. Transverse waves are waves in which the particles of the medium oscillate perpendicular to the directions of the wave propagation. Longitudinal waves are waves in which the particle of the medium oscillate along the directions of the wave propagation. Progressive wave is a wave that moves from the one point to the point of medium to another. The displacement in the freedom for the wave propagating in the positive f direction is given by x comma t equal to f and x minus omega t plus phi. Vary the amplitude of the wave, k the angular wave number, omega is the angular frequency, kx minus omega t plus phi the phase, and phi the phase constant or the phase angle. Wavelength lambda for progressive wave is the distance between two consecutive points of the same phase at a given time. In a stationary wave, it is twice the distance between the two consecutive nodes of the or the antinodes. Period t of the oscillation of a wave is defined as the same at the time any element of the medium takes to move through the complete oscillation. It is related to the angular frequency omega through the relation t is equal to 2 pi by omega. Frequency mu of a wavelength wave is defined by 1 by t and is related to the angular frequency by mu is equal to v omega by 2 pi. A speed of a progressive wave given by v is equal to omega by k, lambda by t is equal to lambda v. The speed of a transverse wave on a stretchy string is set by the property of the string. The speed of the string with the tension t and linear mass density mu is given by v is equal to root over t by mu. Swan wave for longitudinal mechanical waves that can travel through the solid, liquid or gas phase. The speed v of the Swan wave in a fluid having the bulk modulus b and density rho is given by v equal to root over b by rho. Thus the speed of the longitudinal wave in the metallic bar is v equal to root over gamma by rho. For the gas phase, since v is equal to gamma p, the speed of the sound is v is equal to root over gamma p by rho. अब इसका आगे फिर आता है कि when two or more waves travel simultaneously in the same medium, the displacement of any element of the medium is the algebraic sum of the displacement of due to each wave. This is known as the principle of the superposition. Two sinusoidal waves on the same string exhibit different adding or cancelling according to the principle of the superposition. If the two are traveling in the same direction and have the same amplitude a frequency but different in the phase constant phi, the resulting in the single wave with the frequency omega. If phi बराबर 0 at integral multiple of 2 pi, the waves are exactly in the same phase and interference is constructive, and if phi बराबर pi, they are exactly out of the phase and interference is destructive. A traveling wave at the reed boundary or occurred in is reflected with a phase reversal, but the reflection of at an open boundary takes place without any phase change. For incident wave y x comma t equal to a sun x minus omega t, the reflected wave at the ridge boundary y x comma t equal to minus a sun x plus omega t. For the reflection at the open boundary y r x comma t equal to a sun x plus omega t. The interference of the two identical waves moving in the opposite direction producing standing waves. For a string with a fixed end, the standing wave is given by yx comma t equal to 2 sin x cos omega t. A standing wave are created by the fixed location of the zero displacement called the nodes and fixed location for the maximum displacement called the antinodes. The separation between the two constructive nodes or antinodes is lambda by 2. If the shifting of the length L fixed at both the end, vibrates with the frequency given by v equal to nv by 12 जहाँ n होता है 1 2 3. The set of the frequency given by the above relation are called the normal modes of the oscillation of the system. The oscillation mode with the lowest frequency is called the fundamental mode or the first harmonic. The second harmonic is the oscillation mode with n by 2 and so on. A pipe of the length held with one end closed and other end open such as the air columns vibrate with the frequency given by mu is equal to n plus 1 by 2 v by 12 जहाँ n होता है 0 1 2 3. The set of the frequency represented by the above relation are the normal modes of the oscillation of such system. The lowest frequency given by B by 4L is the fundamental mode or the first harmonic. A string of the length L fixed in both ends or air column close to the one end, open at the other end or the open at both ends vibrates with a certain frequency called the normal modes. Each of these frequencies is the union frequency of the system. फिर आता है कि beats arrive when the two waves having the slightly different frequency V1 and V2 and coupled amplitudes are superposed. The beat frequency B2 equal to V1 minus V2. फिर यहाँ पर दिए हुए है कि वेवलेंथ लैम्डा होता है एल मीटर, इसका डिस्टेंस हो गया डिफरेंस बिटवीन टू कंसेक्यूटिव पॉइंट विद द सेम पेज. पॉपुलेशन कांस्टेंट क्या होता है एल माइनस वन एम माइनस वन के इक्वल टू 2 पाई बाई लैम्डा. वेव स्पीड होता है वी एल टी माइनस वन मीटर पर सेकंड और वी इक्वल टू होता है म्यू लैम्डा. बिट फ्रीक्वेंसी बी टी इक्वल टू एल टी माइनस वन एफ माइनस वन डिफरेंस ऑफ द टू क्लोज फ्रीक्वेंसी ऑफ द सुपरपोजिंग वेव से जो दिखाए हुए. फिर अब कुछ पॉइंट्स हैं जैसे वेव इज नॉट ए वेव. A wave is not in the motion of matter as a whole in the medium. A wind is different from the sound wave in the air. The former involves motion of air from one place to other. The latter involves the compression and the reflection of layers of the air. In a wave, energy and not the matter is transferred from the one point to other. In the mechanical wave, energy transfer takes place because of the coupling through the elastic force between the neighboring oscillating part of the medium. Transverse waves can propagate only in the medium when the shear modulus of the elasticity. Longitudinal waves need bulk modulus of the elasticity and are therefore possible in all media, solids and liquids and gases. In a harmonic progressive wave of the given frequency, all particles have the same amplitude but different phases at a given instant of the time. In the stationary wave, all particles between the two modes have the same phase at a given instant but have different amplitudes. Related to the observer at rest in the medium, the speed of the mechanical wave in that medium depends only on the elastic and other properties such as the mass density of the medium. It does not depend on the velocity of the force. अब इसमें कुछ क्वेश्चन है जैसे स्ट्रिंग ऑफ द मास 2.50 kg is under tension of 2 Newton. The length of the stretcher of string is 20 meter. If the transverse jerk is obstructed at one end of the string, how long does the disturbance take to reach the other end? तो मास ऑफ द स्ट्रिंग जो है 2.5 kg, टेंशन है 200 न्यूटन और लेंथ ऑफ द स्ट्रिंग जो है 20 मीटर. तो म्यू इक्वल हो जाएगा एम बाई एल यानी 2.5 बाई 20 यानी 0.125 kg पर मीटर. तो वेलोसिटी भी ऑफ द ट्रांसफर इन द स्ट्रिंग हो जाएगा बी इक्वल टू रूट टी बाई म्यू यानी रूट ओवर 200 बाई 0.125 यानी कितना हो जाएगा 40 मीटर पर सेकंड. फिर आता है टाइम टेकन बाय द डिस्टर्बेंस, तो रिच द अदर एंड हो जाएगा टी इक्वल टू एल बाई बी यानी बी 40 यानी 0.5 सेकंड हो जाएगा. फिर आता है कि स्टोन ड्रॉप इट फ्रॉम द टॉप ऑफ द टावर ऑफ द 100 मीटर high of splash into the water of a pond near the base of the tower, which bend in the splash field at the top given the speed of the sound in air 340 meter per second. So height of the tower is equal to 300 meter. Initial velocity of the stone is equal to 0. Acceleration a is equal to 9.8 meter per second square. Speed of sound in air हो जाएगा 340 meter per second. So the time taken by the stone to strike the water in the pond can be calculated using the second equation of the motion. So f is equal to ut plus half gt square. यानी 300 is equal to t1 is equal to कितना हो जाएगा 1.82 सेकंड. Time taken by the front to reach the top of the tower T2 is equal to 340 and 0.88 second. Therefore, the time after which the splash is here T is equal to T1 plus T2 यानी कि कितना हो जाएगा 8.1 second. फिर next है कि steel bar has a length of 12 meter and the mass of the 2.10 kg. What will the tension in the bar so that the speed of the transverse wave on the bar equals the speed of the sound in the dry air at the 20 degrees Celsius? तो लेंथ ऑफ द स्टील बार हो जाएगा 12 मीटर, मास ऑफ द स्टील बार हो जाएगा 2.10 kg, वेलोसिटी ऑफ द ट्रांसवर्स हो जाएगा 343 मीटर पर सेकंड, और म्यू इक्वल हो जाएगा ML यानी 2.1/12 यानी 0.115 kg पर मीटर। For the टेंशन T, velocity of the transverse can be applied using the relation v equal to root over T by mu, तो T इक्वल हो जाएगा v स्क्वायर म्यू, यहाँ से म्यू निकालेंगे तो कितना आएगा 2.06 न्यूटन। फिर आता है यूज द फॉर्मूला v इक्वल टू रूट ओवर गामा पी बाई रो to explain why the speed of the sound in the air is independent of the pressure, increase with the temperature, increase with the humidity. So take the relation v is equal to root over gamma p by rho, where density rho is equal to mass by volume, m जो है molecular weight of the gas है, v जो volume of the gas है. Hence the equation 1 referred to v is equal to root over gamma pv by m. Now from the ideal equation n is equal to 1, pv is equal to nRT, for the constant t is equal to pv is equal to constant. So in both m and gamma are constant, v is equal to हो जाएगा constant. Hence at a constant temperature, the speed of the sound in the gas is independent of the change in the pressure of the gas. So v is equal to root over gamma p by rho. So from the 1 mole of the gas equation can be written as pv is equal to RT. So p is equal to RT by v. So substituting the equation in the equation 2, v is equal to root over gamma RT by v rho, यानी root over gamma RT by m. तो m is equal to root p rho v is constant हो जाएगा, where gamma and r also are constant. तो we conclude from the equation that mu जो हो जाएगा directly proportional to root t हो जाएगा. Hence the speed of the sound in the gas is directly proportional to the square of the root of the temperature of the gas medium. That when the speed of the sound increase with the increase in the temperature of the gas medium and vice versa. फिर आता है let Vm and Vd be the speed of the sound in the master and dry air respectively. Let rho m and rho be the density of the master and dry air respectively. So take the relation V is equal to root over gamma p by rho. Hence the speed of the sound in the master is Vm is equal to root over gamma p by rho m. And the speed of the sound in dry air is Vd equal to root over gamma p by rho d. On dividing the equation 1 and 2, we get Vm by Vd equal to root over gamma p by rho m into root over gamma p by rho d. तो आ जाएगा root over rho d by rho m. However, the pressure of the vapor density that means rho m जो होएगा वो rho d से कम हो जाएगा, और Vm is greater than हो जाएगा Vd. Hence the speed of the sound in the waft is greater than the air in the dry air. Thus in the gaseous medium the speed of sound increase with the humidity. अगला क्वेश्चन है कि you have learned that traveling wave in the one dimension is given by the function y equal to f x comma t, where x and t must have been the combination x minus bt or x plus bt. That means y is equal to x plus 1 of bt. Either converts to examine the following function of y can partially represent a traveling wave. तो x minus bt का square log x plus bt is equal by x naught 1 by x plus bt. तो no, then not represent a wave, represent a wave, then not represent a wave. ठीक है, ये है जो वेव को रिप्रेजेंट नहीं करता है, ये रिप्रेजेंट करता है वेव को, और ये वेव को रिप्रेजेंट नहीं करता है. तो the converse of the given statement are true. The essential requirement for the function to represent a traveling wave is that it should remain finite for all value of x and t. फिर आता है for x equal to 0 and t equal to 0, the function x minus bt का square becomes 0. For x equal to 0, t equal to 0, the function represents a point and not a wave. For x equal to 0, t equal to 0, log x plus bt by x naught, तो log 0 equal to कितना हो जाएगा infinity. Since the function did not convert to finite value for x equal to 0, t equal to 0, it represents a traveling wave. For x equal to 0, t equal to 0, the 1 by x by bt यानी 1 by 0 is equal to infinity. Since the function did not convert to the finite value for x equal to 0, t equal to 0, it does not represent a traveling wave. फिर आता है कि a bat emits ultrasonic sound of the frequency 1000 kHz in the air. If the sound emits for water surface part is the wavelength of the reflected sound, the transmitted sound or speed of the sound in the air is 40 meter per second and in the water 1480 meter per second. The frequency of the ultrasonic sound दिया हुआ है b is equal to 1000 kHz यानी 10 का पावर 6 हर्ट्ज. Speed of the sound wave b is equal to 40 meter per second. The wavelength of the reflected sound is given by b lambda t equal to b by इतना यानी 340 by 10 का पावर 6 यानी 3.4 10 का माइनस 4. तो फ्रीक्वेंसी ऑफ द अल्ट्रासोनिक साउंड हो जाएगा 10 का पावर 6 हर्ट्ज, और स्पीड ऑफ द साउंड इन द बट हो जाएगा 1480 मीटर पर सेकंड. तो लैम्डा टी इक्वल 1480 बाई 10 का पावर 6 यानी 1.49 मीटर हो जाएगा. फिर आते हैं हॉस्पिटल यूज एन अल्ट्रासोनिक स्कैनर टू लोकेट ट्यूमर इन a tissue. What is the wavelength of the sound in a tissue in which the speed of the sound is 1.5 km per second? The operating frequency of the scanner is 4.2 MHz. The speed of sound in the tissue 1.4 km per second and 1.5 × 14 meter per second. Operating frequency of the scanner was 4.2 MHz and 4.2 × 6 Hz. तो wavelength of the sound in the tissue हो जाएगा lambda equal to b by इतना b by mu यानी 4.5 × 14 by 4.2 × 4 तो 4.1 × 4 minus 4 मीटर हो जाएगा. फिर आता है कि ट्रांसफर हार्मोनिक वेव ऑन स्ट्रिंग इज डिस्कवर्ड बाय x, t equal to 3.05 3050 plus 0.018 x plus 5/4, where x1 by r in the centimeter and t in second. The positive direction of x is from the left to the right. Is this a traveling wave or a stationary wave? If it is traveling wave, what are the speed and the direction of its propagation? What are its amplitude and the frequency? What is the initial phase and the origin? What is the least distance from between the two successive craft in the wave? तो यस स्पीड बराबर हो जाएगा 20 मीटर पर सेकंड, डायरेक्शन राइट टू द लेफ्ट 3 सेंटीमीटर 5.3 यानी 5/4 और 3.49 आ जाएगा. तो the equation for a progressive wave traveling from the left to the right is given by the displacement function yx format is equal to f sin omega t plus kx plus phi. The given equation by x format is equal to हो जाएगा 3.0 sin 36t plus 0.08 1x plus pi/4. On comparing both the equation, we find that equation 2 represents a traveling wave propagating from the right to the left. So using equation 1 and 2, we can write omega is equal to 36 rad, k is equal to 0.01 per meter. So b naught v is equal to omega by 2 pi यानी lambda by 2 pi by k. Also v is equal to v lambda. तो यहाँ से निकालेंगे तो v is equal to कितना आ जाएगा omega by k. तो 36 by 0.08 equal to 2000 सेंटीमीटर पर सेकंड एंड 20 मीटर पर सेकंड. Hence, the speed of the given traveling wave is 20 मीटर पर सेकंड. Amplitude of the given wave is equal to 3 सेंटीमीटर. तो frequency of the given wave हो जाएगा v is equal to omega by 2 pi यानी 36 by 2 मतलब 3.14 यानी 4.43 हर्ट्ज. On comparing equation 1 and 2, we find that initial phase phi is equal to pi/4. The difference between the successive craft of f equal to the wavelength of the wave. The wavelength is given by k is equal to 2 pi by lambda. तो lambda is equal to 2 pi by k यानी 3.49 मीटर. फिर आता है कि for the wave described in equation 515.8, plot the displacement by perfect t graph for the x y equal to 0 or 2 or 4 centimeter. What are the shape of this graph? In which aspect that the oscillating motion is traveling wave differ from the one point to another, amplitude, frequency or phase. So all the graphs for the different phase, the given transverse harmonic wave is yx format equal to 3 sin 36t plus 0.018x plus pi/4. For x equal to 0, the equation reduced to y 0, t equal to 3 sin 36t plus pi/4. Also omega is equal to 2 pi by t and 36 rad per second. So t is equal to कितना आ जाएगा pi by 8. Plotting by perfect t graph using different value of t listed in a table. So 0 for x for 0, x for 2, x for 4, the phase of the three waves will be changed. This will be called amplitude and frequency are invariant of any change in the x. The party plots of these three waves are shown in the figure. उसके बाद अगला क्वेश्चन है कि for the traveling wave harmonic wave yx format 2.0 cos 2 pi 10t minus 0.08 x plus 0.35, where x and y in the centimeter, t in the second. Calculate the phase difference between the oscillatory motion of the two waves divided by distance of 4 meter, 0.5 meter, lambda by 2, 3 lambda by 4. The equation of a traveling harmonic wave given by yx format equal to cos 2 pi 10t minus 0.080x plus 0.35. Propagation constant k is equal to 0.0160 pi, amplitude a by 2 centimeter, and the frequency omega is equal to 20 pi rad. Phi equal to kx equal to pi by lambda, x equal to 4 मीटर यानी 4 सेंटीमीटर, phi equal to 6.4 pi. अगर यहाँ से निकालेंगे तो 0.5 मीटर 50 सेंटीमीटर, phi equal to 0.016 pi यानी 50 गुना 0.8 pi. x equal to lambda by 2, तो phi equal to 2 lambda by 2 यानी lambda by 2 equal to pi rad. तो x equal to 3 lambda by 4, तो phi equal to 2 pi by lambda यानी गुना 3 lambda by 4 equal to 1.5 pi rad. अगला क्वेश्चन है कि द ट्रांसफर डिस्प्लेसमेंट ऑफ स्ट्रिंग क्लैम्पेड एट बोथ एंड गिवन बाय x फॉर्मेट इक्वल टू 0.06 sin 2/3x cos 120 pi t, where x and y are in the meter and t in the second. The length of the string is 1.5 meter and mass is 3.3 गुना 10⁻² kg. Answer the following that the function depends the traveling wave of the stationary wave. Interpret the wave as a superposition of the two waves traveling in the opposite direction. What is the wavelength, frequency and the speed of each wave? Determine the tension in the string. So the general equation depending the stationary wave given by the displacement function yx format equal to 2 sin kx cos omega t. This equation is similar to the given equation yx format equal to 0.0 sin 6 to x by 3 cos x of base by t. And the given function represents a stationary wave, a wave traveling along the positive direction given by y1 is equal to a sin kx omega t minus kx. The wave traveling along the negative direction is given by y2 equal to a sin omega t plus kx. The proposition of due to each wave gives minus 2 a sin 2 pi by lambda x cos 2 pi by into vt. तो यहाँ से निकालेंगे तो ट्रांसफर ऑफ डिस्प्लेसमेंट ऑफ स्ट्रिंग गिवन बाय x फॉर्मेट इक्वल टू 0.056 2 pi x by 3 cos 120 pi t. कंपेयर करें इक्वेशन 1 and 2 को तो 2 pi by lambda x equal to 2 pi by 3, so lambda equal to lambda equal to 3 meter. It is given that 120 pi equal to 2 pi v, तो v equal to 60 hertz और speed v equal to v lambda. तो 60 to 3 equal to 180 meter per second और v equal to root over 3 there velocity of the transverse v equal to x of meter per second, mass of the string m equal to 10⁻⁴ -2 per kg और लेंथ ऑफ द स्ट्रिंग L इक्वल टू 1.5 मीटर। तो मास पर यूनिट ऑफ स्ट्रिंग हो जाएगा म्यू इक्वल टू M/L, जहाँ पर इतना हो जाएगा 10⁻10 T एप्लीकेशन 10⁻10 T इक्वल टू बी स्क्वायर बाई म्यू, तो आ जाएगा 684 न्यूटन। नेक्स्ट है कि for the wave on the string described in example 515.11 to all the points on the string oscillate with the same frequency of phase and amplitude. Explain the answer but in amplitude of the point 0.315 meter away from the end. The yes except at the nodes, yes except at nodes or no. So all the points on the string oscillate with the same frequency except at the nodes which have the zero frequency. All the points in the vibrating loop have the same phase except at the nodes. All the points in the vibrating loop have the different amplitudes of the vibration. The given equation is by x over t equal to 0.06 find 2 pi x by 3 cos x by 5t. For x equal to 0.315 t equal to 0, amplitude equal to displacement equal to 0.06 sin 2 pi by 3x cos 0 यानी 0.06 2 pi by 3 0.315 into 1, तो यहाँ पे आएगा कितना 0.042 मीटर आ जाएगा। फिर आता है अगला क्वेश्चन, given below the function of x and t to remain a displacement transfer for the general of an elastic wave after it be the independent of traveling wave, if stationary wave or none at all. तो y इक्वल टू कॉस 2x 3x sin 10t y इक्वल टू रूट x माइनस bt y इक्वल टू 3 5x माइनस 0.5t प्लस 4 cos 5x माइनस 0.5t और y इक्वल टू cos x sin t cos 2x sin 2t। तो यहाँ से निकालेंगे तो आता है the given equation depends on stationary wave because the harmonic term kx and omega t appears separately in the equation. The given equation does not contain any harmonic term, therefore it does not depend either traveling wave or stationary wave. The given equation depends on traveling wave and the harmonic terms kx and omega t are in the combination kx minus omega t. The given equation depends on stationary wave because the harmonic terms kx and omega t appear stationary in the equation. The equation actually represents the superposition of the two stationary wave. फिर आता है कि bar of touch between two rigid supports vibrates in a fundamental node with a frequency of the 45 Hz. The mass of the bar is 3.5 × 10⁻²2 kg and its layer mass density is 4.0 × 10⁻²2 kg per meter. So what is the speed of the transverse wave on the string? The tension in the string. तो मास ऑफ द बार m इक्वल टू 3.5 × 10⁻² kg दिया हुआ है। लिनियर मास डेंसिटी म्यू इक्वल टू m/l यानी 4 × 10⁻² kg per meter। फ्रीक्वेंसी ऑफ द वाइब्रेशन 45 हर्ट्ज। l इक्वल टू m/u यानी 0.815 मीटर दिया हुआ है। तो वेवलेंथ ऑफ द स्टेशनरी wave lambda related to the length of the bar by the elephant L lambda equal to 2l/n, where n जो है number of the node in the bar है। For the fundamental node n equal to 1 तो lambda equal to 2l तो lambda equal to 1.15 मीटर आ जाएगा। The speed of the transfer of stringing by b equal to b lambda यानी 48.15 मीटर पर सेकंड। The tension produced in the stringing by t equal to b square by mu यानी 48.06 न्यूटन। फिर आता है कि meter long tube open at one end with a movable piston at the other end. So given fixed frequency force when the tube length is 25.5 cm or 29.3 cm. Estimate the speed of the sound in the air at the temperature of the experiment. The age effects may be neglected. The frequency of the tuning for a B is equal to 340 Hz. Since the given pipe is attached with the piston at one end, it will behave as a pipe with one end and other end closed open. Such a system produces odd harmonics. The fundamental note in the closed pipe is given by L1 equal to lambda by 4. Length of the pipe L1 equal to 25.5 cm and 0.255 meter. Lambda is equal to 4l1 यानी 4.02 मीटर। तो स्पीड ऑफ द साउंड गिवन बाय द गिवन v इक्वल टू पी लैम्डा यानी क्या आ जाएगा 340.8 मीटर पर सेकंड। फिर आता है स्टील रॉड 4 मीटर लॉन्ग क्लैम्पेड मिडिल द फंडामेंटल फ्रीक्वेंसी ऑफ द लॉन्गिट्यूडनल वाइब्रेशन ऑफ द रॉड गिवन बाय 2.53 किलोहर्ट्ज। तो व्हाट इज द स्पीड ऑफ साउंड इन द स्टील? तो लेंथ ऑफ द स्टील रॉड L इक्वल टू 4 सेंटीमीटर इक्वल टू 1 मीटर। फंडामेंटल फ्रीक्वेंसी ऑफ द वाइब्रेशन v इक्वल टू 2.53 किलोहर्ट्ज और 2.53 × 14 हर्ट्ज। So when the rod is plugged at the middle and anti-node is formed at the center, nodes are formed at two ends as shown in the figure. Distance between two nodes is lambda by 2, so L equal to lambda by 2, so lambda equal to 2L or 2 meter. The speed of the sound is still given by P equal to V lambda यानी 2.53 × 14 × 2 यानी 5.06 किलोमीटर पर सेकंड आ जाएगा। फिर आता है कि पाइप 20 cm long is closed at one end, which harmonic mode of the pipe is uniquely excited by chance of 30 Hz. Will the same force be units with the pipe if both ends are open? A speed of the sound in the air is 340 meter per second. So first fundamental no. Length of the pipe L equal to 20 cm and 0.2 meter. Force frequency and normal mode of the frequency Bn is equal to 430 Hz. A speed of sound हो जाएगा b equal to 340 meter per second. In a closed pipe, the nth normal mode of the frequency given by the elephant Bn is equal to n minus 1 b by 4l. तो 430 equal to n minus 1 340 4 0.2. तो n minus equal to 1. Hence the first mode of the vibration is affected by the given force in a pipe open at both ends. Nth mode of the vibration frequency given by the elephant Bn is equal to n by 12. तो n equal to हो जाएगा 12 b bn by b यानी 0.5. Since The number of the mode of the vibration to hide integer, the given source does not produce a unit vibration in the open pipe. अगला question. Two filters of string A and B playing the note Ga are slightly out of the tune and produce a beat for the frequency which is 6 kHz. The tension of string A is slightly reduced and the beat frequency of the found to be 10 kHz. If the original frequency of A is 40 Hz, but the frequency of the B, the frequency of string A F is equal to 24 Hz, frequency of string B FB, beat frequency equal to 6 Hz. So N is equal to FA plus minus FB, तो F6 equal to 24 plus minus FB, तो FA equal to 340 Hz और 318 Hz हो सकता है. So frequency decrease with decrease in the tension of string. This is because frequency directly proportional to the square root of the tension. It is given by V directly proportional to root T. If the bit frequency cannot be 330 किलोहर्ट्ज नहीं हो सकता है तो Fn इक्वल टू आएगा 318 हर्ट्ज. आगे का देखते हैं. Explain why or how in a found force a different node is a preferred node and vice versa. Pets can ascertain distance, direction, nature, and the size of the effect without an edge. A violin note and the sitar note may have the same frequency, yet we can distinguish between the two notes. Solids can support two longitudinal and transverse waves, but only longitudinal waves can propagate in the gas phase, and the shape of the pulse gets distorted during the propagation in a dispersive medium. तो इसका आंसर है कि node is present where the amplitude of the vibration is minimum and the periphery is the maximum. On the other hand, an antinode is present where the amplitude of the vibration is maximum and the periphery is minimum. Therefore, dispersion node is nothing but the peripheral antinode and vice versa. Bats emit very high frequency ultrasonic and sound waves. These waves get reflected back towards them by the obstacle. A bat receives a reflected wave frequency and estimates the distance, direction, nature, and the size of the obstacle with the help of the brain, its brain senses. The overtone produced by the sitar and the violin and the strength of these overtones are different, hence one can distinguish between the notes produced by the sitar and the violin even if they have the same frequency of the vibration. Solids have the sphere modulus, they can sustain a sharing of waves. Since fluids do not have any finite shape, they yield to the sharing of waves. The propagation of the transverse wave in such that it produces sharing of waves is a medium. The propagation of such a wave is possible only in the solids and not in the gas phase. Both solids and the fluids have their respective bulk moduli. They can sustain compressive waves and longitudinal waves can propagate through the solids and the fluids. A pulse is actually a combination of the waves having the different wavelength. These waves travel in the dispersion medium with different velocity depending on the nature of the medium. This results in a distortion of the shape of the वेव पल्स. तो यहाँ पर है जो वेव चैप्टर है जो कंप्लीट होता है. सही है.